the importance of or the impact of defect passivation on the performance and stability of perovskite solar cells, and we'll try to answer the questions. Which part is more problematic, the interface or the bug? At the end of the presentation, we should answer that question. So first, I will start with the first point, which is the quest for clean and renewable energy sources. So as you know that actually today we are consuming 18 terawatt, and the target in 2050 we are going to actually we consume more 30 terawatt, and according to the Shell actually analysis in 2070 we are going to consume 50 terawatt, which requires us to find a source where we can provide energy. So as you know that actually energy sources can be divided in two types, renewable and renewable sources. Non-renewable sources unfriendly to our environment and not sustainable and will run out at the end. Example like oil, coal, etc. Also, it's behind the population and the climate changes. Renewable sources, and this is what we are looking for, clean and abundant and friendly to our environment and also sustainable, like solar energy and hydroelectric, etc. Unfortunately, our main current produced power is coming from the non-renewable sources, which I mean today, like we are producing like 0.5% of solar PV, where we should contribute like 33% of solar PV in 2070, about like 17 terawatt. Our objective is to focus on the energy demand crisis that requires sustainable resources, and one of the most effective way is to harvest the energy of the sunlight in PV technology. So that means our challenge is terawatt energy. So here just I think Dr. Mustafa yesterday showed this figure, so I will just skip, but just I will go to one point just to show the importance of the solar. So we can see that we are receiving on the earth actually it's 1.2 10 power 5 terawatt. So if we cover the whole land, actually we are going to extract like 36 terawatt, but this is impossible because we need a place where we can live. But just here to show you the importance of the the solar. So that means the best way is to harvest the sunlight to have a clean environment. So for the evaluation of photovoltaic technology, first I would like to give like a basic science behind the PV technology. So we can see here, this is the spectrum of the the sunlight. So we'll focus on the 1.5 global. So if once we are, when we want to design a material, we have to take into consideration the band gap of the material. We cannot bring any material and we can say, okay, we'll use it for PV technology. So we can see clearly here the spectral radiance as a function of the wavelength. According to the wavelength, we can design the material, and like perovskite material is a semiconductor material. A semiconductor material is located between the insulating and the conductor state, which is there is a band, what's called a band gap. It's the difference between the gray box represent the valence band and the empty box, it's the conduction band. So once we shine the material that we design according to the spectrum, actually we are going to first to absorb the light, then we will generate the carriers. If we connect it to the external circuit, that means we'll have what's called the current flow, then also will produce the voltage. At the end we'll produce the power. So we put like power in and we get power out. So it's very important, actually, as I mentioned to you, we have to design a material. We have to take into consideration the band gap from the solar spectrum, and this is simply how it works. The material, if we use it for PV technology, then we'll translate this one. Actually, what I showed here, we'll translate it to IV curve. The IV curve, it's very important to understand it. Actually, here's the VOC. The VOC means is the open circuit voltage, means the highest voltage we can get once the current equal to 0. And also the GC, or the short circuit current, it's the highest current we can get when the voltage equal to 0. From these parameters, then we can calculate the efficiency. But we cannot deliver a power at the VOC or the DC. This is not the real operation. If we want to operate the solar cell in real operation, so that means we have to take it at the maximum power point, where the voltage maximum at the same time we have the maximum current, because if we take it at the VOC, that means the power will be equal to 0. So it's just the efficiency to have it to compare our technology to others. For example, to compare perovskite to gallium arsenide, to compare the perovskite also to the silicon, and etc. So the question now, what's the highest efficiency we can reach? According to the Shockley-Queisser limit, I don't want to go here in details, but you can search about that. It's known as Shockley-Queisser limit. From the Shockley-Queisser limit, we can see that clearly we can reach to the highest efficiency for single junction. That means we have single absorber layer. It's 32%. It's ranging between 1.2 to 1.4 electron volts. As I showed you in the previous slide, band gap, it's very important to be considered once you are designing a material for the PV technology. So we can see here actually we have different generations. Wafer-based like monosilicon, now the highest its efficiency is 26, but also the polycrystalline also reached 23.3, and gallium arsenide is the highest, it's 27.8. And also we can see from the thin film or the thin films of the second generation cadmium telluride, it's reaching like 22, and the CIGS, it's like 23.4, and etc. So we can see from the third generation also the emerging thin films, and the perovskite is one of them. What we'll talk about it today. It's reached now to 25.7 or 25.9 to correct it, because I didn't update it yet. So this is, we have like different technology, and I will talk today mainly about the perovskite solar cell. And there is more advanced concepts like, quantum dot. So to evaluate any technology or to design a technology, you have to take 3 parameters into consideration, which is known as cost, efficiency, and lifetime. So what you have to do a compromise between these 3 guys, the cost and the efficiency and the lifetime, for to consider it for commercialization of PV technology. So here I would like to to show you the material complexity. Actually, if we take it from the middle and we go to the left side, we can see that clearly, yes, we are having simple materials, but we are going for like a complicated process, and we need like clean energy, and that means it's costly. So that means we need like advanced system, and the process also very complicated. We need to do a lot of dopings. So, but if we compare that from the middle to the right side, or specifically to the emerging thin films, we can see that clearly, yes, the material will become more complicated, but the process will be very simple and reachable, and also tolerant to defects, and also the cost is not high as compared to the left side. Also, you know that actually if we manufacture any technology with the high temperature, that means we are limited to, specific applications. And also we can see that with the cost will go very high. If we take, for example, silicon, the typical temperature we can reach over 800 degrees. But if we compare, for example, to perovskite, we can see that clearly we can fabricate the perovskite even at below 200 degrees. Also, now there are some works show that we can fabricate it also at 100 degrees, which give us to apply to more applications like flexible substrate or lightweighting. So we can like do more, applications as compared to this technology, which can be fabricated at high temperature. So if we also, the extraction of the raw material, if we compare, like, for example, start with silicon. So to reach the target of 2050, we need 6 years to produce the, the raw material for the, for the silicon. But if we compare also to the cadmium telluride, specifically for the TE, we need like more than 1,000 years to produce the raw material. But if we compare it to the emerging technology, like, for example, like specifically perovskite, as it's the main topic today, So we can see that within 3 years, we can produce the raw material of the perovskite. This is what makes the emerging thin films, specifically the perovskite, very promising, and interesting and really promising candidate MBV technology. So here I would like to start with a brief introduction about the perovskite, about the perovskite solar cell, or sometimes we call it like organic, inorganic metal halide perovskite, depends on your composition. So it's following this formula, which is known as a 3D perovskite. A stands for like methylaminium or methylaminium or formidinium or cesium, and B like metals like lead, tin, and X for like chloride, bromide, iodide. So then you will you will make your composition according to this formula. Actually, perovskite it was known actually even before 2009, but in 2009 actually when Prof. Miyazaki, if I pronounce his name correctly, he showed that actually perovskite is a very good candidate to be used as absorber layer for PV technology. From that work, the efficiency what he showed, Prof. Miyazaki, was about 3.8%, but we can see that clearly within a decade now, the efficiency now, the record efficiency is 25.9. Within a decade, just jumped from 3.8 to close to 26%. Why? Because perovskite has some interesting properties, such as high absorption coefficient, direct band gap, and its band gap can be easily tuned, and also small exciting banding, and also ambipolar, with the hole and electron diffusion length. Now we can see from the literature exceed like 1 micro, and also it can be easily proceed by solution at low temperature and tolerant to defect. So here just I would like to show you in this figure just the number of publications just up to like last February. The number of publications reached to more than like 22,000 articles in total. So if we compare the efficiency, as I mentioned, within almost around a decade, it's jumped from 3.8 to like 20, close to 26%. But if we compare it to silicon, it took many years to reach to 26%, which makes the gap between them like less than 1%. And this is what makes the perovskite a very interesting material because of its interesting properties, as I showed in the previous slide. So here the work principle for the perovskite. Just I would like to show you the cartoon, then I will show you the real image of the cross section. So here what we do, we have like a glass coated with a conductive layer, it's known as FTO. Then we deposit the compact, we call it the ETL, the electron transport layer. Then the perovskite, after that we deposit like the spire, we use it as a whole transport layer, then the electrode. But let me show you with the real cross section for the perovskite. We can see here's the perovskite. So here's the transport electrode, and here's the electron transport layer, and this is the perovskite, and here is the transport layer, and then the electrode. So as I mentioned in the previous slides also, once we eliminate the perovskite or the perovskite as absorber layer, we are going to generate the carriers. Then after the absorbance, then generation. After that, we'll get to extract these carriers by these different transport layers. We can see that clearly the perovskite, it's sandwiched between two interfaces. One interface with the whole transport layer, and the second interface with the electron transport layer. And what I tried since the end of 2016, actually, I did a lot of work for the defect passivation. And the question I want to show you, we want to answer it together today. Which part is more problematic? Actually, the bulk or the interface? Because here I didn't work, but I start some working now. But I will talk about only the interface with the whole transport layer and the bulk. So which part is more problematic? The bulk, the defect in the bulk, or the defect at the interface? Because as we know that actually, at any interface, especially if it's axial growth, so that means we have like a high probability of losing the carriers at the interface due to the non-radiative, will have like non-radiative recombination at the interface. So because of the traps, So that means I will show you today which part is more problematic, the interface or the bulk. From some of my works, I will show you today. So let's come to the main message I want to show you today. The impact of the defect passivation on the performance and the stability of the perovskite. So perovskite material, it's like any semiconductor material. It contains, different defects actually. It can be vacancies or interstitial or anti-sites, from shallow to deep traps. It depends on the formation energy. So also it has some surface defects. It could be like anti-sites, uncoordinated lead or lead cluster or iodide vacancies or organic A-site cation or uncoordinated iodide. The good thing about perovskite, majority defects for shallow traps, and shallow trap is located at the band X with the conduction band and the valence band. And also these shallow defects, yes, they cause less performance, loss, or they have less effect on the performance, but they have a very bad effect on the long-term stability, because these shallow defects, they can do what's called migration within the bulk and also to the interface, and they can create like a path of degradation, and at the end will end up with like a very bad device. And we have to take care of these points, which means we have to have like a very or a highly efficient and stable device. These defects must be pacified. So in fact, there are many strategies used to mitigate these defects, like using like compositional engineering, like depositing like a layer on top of the 3D perovskite to make like a hetero structures, or incorporation of dopants, as Dr. Mustafa showed you yesterday, and also halide management, or used like at the bulk or at the interface like ammonium salts or ionic additives or Lewis acid or base. So there are many strategies, and also if we check the literature now, we can see like many works, many additives used to pacify the defects. So here just I would like to show you some of my works since the end of 16, when I start using, when I focus on the defect pacification work. Actually, you can see clearly the efficiency improve. Up to today we have something but not reported yet. We reached to 25.4%. I will show you today some of my works, just 3 of my works, to show you the importance of defect pacification. So the first work I would like to show you, this is why this work done like at the end of 2018, and we published it also in Nature. So what I did in this work, I only now pacified the interface. I didn't touch the bulk. So just the treatment only for the interface. I used 3 different ammonium salts, namely as ethylammonium iodide and guanidinium iodide, and also imidazolium iodide with different structure, and also ionic radium. So what we did for the the fabrication, first we have the ETL layer. Once we prepare the ETL layer, we deposit the perovskite solution or precursor. After that, we drop the anti-solvent to have the intermediate phase. Then we do the annealing to form the 3D perovskite. Then we cool it down to room temperature. After that, I pacified it, whether ethylammonium or guanidinium or imidazolium, and then I did a second annealing just to evaporate the solvent. Then we did we deposit the whole transport layer or the HTM, then the gold, then we measure the device. This is the composition what I used. So I will repeat it again. Here in this project, I just do the interface treatment between the perovskite and the HTM. We found from this work actually ethylammonium showed the best efficiency. In 2019 was very good actually. It was very high efficiency, like 22.4%. But not only if you have high efficiency, that means that the work is done. No, because perovskite, I know it faces some problem for the stability. So we need to also have both high efficiency or high performance at the same time. Also, we need to enhance the stability. Then what we did here, actually, we subjected these devices to under one sun illumination at the maximum power point in nitrogen environment at room temperature, and we can see clearly after 500 hours, ethyl ammonium iodide showed the loss of only around 5% as compared to others. That means ethyl ammonium iodide not only enhanced the performance, but also the stability. So the second question for us that time, actually, what's the mechanism at the interface? How this ethyl ammonium pacifies the interface? Then we did for the first time, actually, the 2D solid state NMR, means we have the film and we scratch the film and we did NMR for the powder. So we can see here clearly, actually, there are three peaks. To understand these 3 peaks, this is our control. If we compare, sorry, I didn't make it well, but if we compare A to E now, we can see clearly that there are 3 new peaks. To understand from where these 3 peaks come, so what we did here, first we did only ethyl ammonium iodide, and we found actually there is no matching with these 3 peaks. Then we did ethyl ammonium, only ethyl ammonium lead iodide, and we can see there is a good matching. But we believe that as long as our composition contain it's rich, formidinium, we believe there is interaction between the ethyl ammonium and the formidinium. Then we did solid state NMR, and we found also still there is like a good matching between them. But the question now, it's clear that there is a secondary layer formed on top of the perovskite. But to prove our hypothesis, is there interaction between the formidinium and the ethyl ammonium? We did 2D solid state NMR to see both ethyl ammonium and formidinium at the same environment or not. If they are in the same environment, that means they did interaction. We can see clearly the ethyl ammonium with the formidinium, they are in the same environment, which prove our hypothesis. That means there is a secondary layer formed on top of the 3D perovskite. The conclusion of this work, we can see clearly ethyl ammonium iodide not only enhance the performance, but also improve the stability. And this work also, we publish it in Nature Energy. So if you want to have like more details, you can find the, you can see the paper, and also it's open access. So now I showed that actually the interface is very important to pacify it. What I did for the second work also, I want to check now bulk. Is it problematic like the interface or not? What I did here in this work, I kept the interface pacified by the ethyl ammonium iodide. Then now I will treat the bulk itself. Bulk means the precursor solution when we formed the perovskite. As we know that actually the bounding between, this is the hypothesis, or this is how I designed the work actually. So we know that actually the bounding between the lead iodide actually it's very weak and can be easily broken. If it gets broken, that means we'll have lead will become like metallic lead, and metallic lead also lead zero. It's already proved in the literature also. Not only can create like defects or have like deep defects to enhance the non-radiative recombination, but also can create a path of degradation. So it's very bad. We need to stop it. By our treatment. The same thing for the iodide. What I did here, because we can see clearly, like in 2017, if I'm not mistaken, when Prof. Siok, I pronounce his name correctly, he showed that actually mixing I2 with the isopropanol, this will lead to that what's called triiodide, and he showed that actually it can pacify the defects, and he got the certified efficiency around 22.1. What I did here, because I said, okay, so we have methyl ammonium iodide. Why not use methyl ammonium triiodide? Because we are already using methyl ammonium iodide in our composition. And what I did here, I mixed methyl ammonium iodide plus I2 plus isopropanol to to perform methylaminium triiodide. Then I mix it with the precursor solution for a couple of reasons. First, methylaminium iodide can help me to stabilize FAPI, or sometimes we call it FAPI, or means formidinium lead iodide. And second thing, the triiodide can passivate the defects. So this is our composition. So what I did here, we can see clearly the efficiency improved up to 23.5%. That means, and also the fill factor we can see clearly, and the VOC improved. The fill factor was above 81%, and also the VOC improved. So what I did also here, because as I mentioned, all the time we have to connect the performance to the stability. We cannot do like say, okay, our performance is good and finish. No, we have to check the stability. What I did here, I did 3 different tests actually. Here in dark, 10% with the relative humidity. And also here, like we store the device at 55-degree temperature and measure it from time to time. And in the third test, what I did here, actually, I kept the device under 1 sun illumination at maximum power point in nitrogen environment at room temperature. So we can see clearly from all these 3 tests, different tests actually, our target means with them, the treatment with the methylaminium triiodide, it showed efficiency much better than the control, which means improve the stability as well as the efficiency. So as I mentioned to you, actually, when we saw like we have like a high fill factor, we did like to study the charge transport to check the mobility. And we can see the mobility as a function of different fluence here. We can see clearly, from our target or after the addition of methylaminium triiodide, the mobility improved, as well as the photo conductivity, which means methylaminium triiodide additive enhances the charge transport properties. Also, we check the recombination analysis. We can see that from the BLQY or the photoluminescence quantum yield after the addition of methylaminium triiodide, the BLQY improved from 0.6 to 1.5, as well as also for the TRBL, which means that methylaminium triiodide not only improve the efficiency and the stability, but also improve the charge transport, as well as suppress the non-radiative recombination. So the conclusion from this work, we can see that clearly methylaminium triiodide, we use it as an additive to passivate the defects, enhance the power conversion efficiency of around 23.5% with the high fill factor over 80%. So as the same thing for the previous work, if you want more details, you can see the paper, it's already online. So we can see clearly now from the first work and the second work, I showed that actually both very important, the interface and also the bulk. But you can see clearly my efficiency is still like below, I would say like a state of the art, because 23 point close to 23.5 is still below like 25%. So then what I did the same thing, but I designed a material. We designed it actually at EPFL with the help of my colleague, Dr. Lucas. So we did here actually, passivation for, the bulk and the interface at the same time. And this work already now under revision in June. And also we felt like a patent for this work. And also it's not actually online yet, but I don't want to go in details for this work, but just I will show you, the idea of this work. So what I found actually, we can see from the literature and also the certified efficiency, also some efficiency showed 25%. They said like octylaminium iodide is the best, and this is the commonly used pacivator. Then I asked it actually, does it come from the aminium or from the shell length? So what I did, I redesigned this additive actually. First, we divided into 3 stages. The first stage, we changed the size of the head group and we select the best. After that, we change the length and we select the best. After that, we check with different, halide counter like fluoride, bromide, and iodide. So then I found actually dimethyl octylaminium when I added in the bulk and dimethyl octylaminium fluoride on the surface, it showed, showed the best actually. Then we reached to efficiency over 24%, 24.9. And also I used a very interesting composition in this project. It's known as formidinium lead iodide with the band gap of 1.53 electron volt. And also the same thing I subjected to, at the maximum power point under, one sun. And we can see that clearly, like after 1,200 hours, just a 10% degradation of the initial BC. So also I did the PLQY. We can see clearly actually improved from 0.03 for the control, and for the treated devices, actually we can see that clearly improved up to 2.9%. But also we tried using the DFT and collaborating with Prof. Ursula from EPFL to understand why the dimethyl octylaminium showed the best actually. Then from the DFT, we can see that clearly due to the symmetry of the additive. Actually, it's covered much. It covered the surface much better than octylaminium. We can see clearly from the figure here. So it showed like better coverage than others. And this is also can explain the enhancement of the stability of our device. So the summary of the conclusion from all the work, or to answer the question what I mentioned at the beginning of the presentation. So first here I employed like different strategies based on organic ammonium salts to engineer the bulk and the interface, or to see which part is more problematic actually. Also, I did like in-depth investigation for the optoelectronic and the structural morphological properties. So to answer the question actually, and also to make it clear, I can see that from the result what I got, actually both very important to be passivated, the bulk and the interface, to obtain a highly unstable device for perovskite solar cell. So here also I would like to thank first Prof. Michael Kratzel and for supervising me, and also Dr. Zakir Eddin and my colleagues from EPFL like Dr. Thomas, George, Lucas, Felix, and Anurag Krishna. And also would like to thank Prof. Ursula for her, for her help for the DFT calculation. Also Prof. Linden for the NMR, and also Prof. Moser for the terahertz measurement. And also would like to thank King Abdulaziz for science and technology. Also would like to thank our team from CAX, Dr. Abdullah and Megad, and also Park and Khola. And I would like to thank you for your attention. I would be more than happy to answer any question. Thank you again.
Thank you very much, Essa, for the very interesting and inspiring presentation on how to reach more than 25% power conversion efficiency for perovskite solar cells. So I can see some questions in the chat, and please also for the audience raise your virtual hand in case you want to ask any questions. So I will go very quickly to the first question, which is coming from Nisheka Anand Kat. How do you select salts, EAI, etc., to passivate? On what criteria? What solvents do you use for preparing the solution?
So first of all, actually, whether for the ethylaminium or the guandinium or with the imidazolium, at the beginning, actually, when I designed the project, the idea was to use guandinium iodide because that time it showed, the best due to the more hydrogen bonding actually. But then I applied at the beginning actually the idea to apply them into the bulk. Then I found actually in the bulk they didn't work. Yes, VOC was improved, but fill factor and also the the fill factor and the current dropped a lot. And I believe that they formed like a barrier layer within the green boundaries or one of the interface. But then actually I selected them because they have with the different size and different structure. But to be honest, it's very difficult to say there is a specific criteria to use to passivate, but sometimes you need to see, I mean, also from the previous work, then you have to design your own, I mean, work actually. But no one can tell you use this one to work, but also you need to understand the perovskite, what kind of defects in the perovskite. So the solution I use to passivate, actually, it's isopropanol, because we use it with to spin coat the film. As long as we are using a dynamic way, I think isopropanol cannot affect the film. But if he meant like for the perovskite, we use DMS solution.
Thank you for the question, and Issa for the answer. Let's go to the next one, which is coming from another Saudi guy, Timur Maksudov. So the question is the following. Thank you for the interesting presentation. And the question is, based on what criteria do you choose which molecule to use for passivation?
Yeah, so as I mentioned to the previous, the previous question, actually, it's honestly, very difficult to select. But as I mentioned, we have to understand because you know that actually we are using like a soft material. The perovskite is a soft material, and also we know that it's a mixture between like organic and inorganic material. There are many parameters can affect the perovskite. Maybe it can be the synthesis. The synthesis can also create defects. Also, maybe can be geometric or not geometric, and also can be like due to the annealing or the post annealing, because you know some cations and also iodide, they can evaporate from the surface. So you can mainly, I would say, if you see my work, I focus on the ammonium salts because I was believing, like, for example, if I'm using ethyl ammonium iodide, this can passivate the negative defects, and the iodide, it can passivate the positive defects. But to say like there is one rule, this is very difficult actually to say. But you have to understand your material, and also we can see that clearly. Also depends on the composition. Because at the end, because when you growth the material, you don't know what you will end with. Then you don't know exactly what kind of defects you will have at the surface.
Okay, thank you for the answer. And the next question is from Alexander. Great presentation. Which technique do you use for passivation? Is it CVD? Okay, I think this question is already answered.
Mm-hmm.
So I think, Alexander, your question is already answered. From Essa Kalasaria Nikhil. So the question is the following: with your devices, have you ever seen unreactive or excess lead iodide leads to high degree of JV hysteresis?
Actually, I noticed that from all the passivation, hysteresis can be, minimized due to the passivation action. But for the excess, we can see sometimes from the XRD. Before the passivation, we can see a peak of lead iodide, like it's not reacted actually, but once we passivate it, we can see clearly the peak completely disappear. That means sometimes also, and sometimes we need to use some excess of lead iodide. It can help also for the bonding at the interface with your additive to passivate the process.
Thank you for the answer. And another one is, thank you, Essa, fascinating journey into defect passivation. From Felix Utama, for your third work, it looks like the iodide passivator works best for bulk defects, while the fluoride one is best for surface interface defects. Can you comment on the possible causes for that difference? Thank you.
Yeah, actually, I found that actually when I did actually the passivation engineering, actually first, as I showed you actually in the slide, actually we use different like fluoride, bromide, and iodide. I found actually, the best actually was in the bulk, as you mentioned also in here question, was iodide, but on the surface was fluoride. But I think because fluoride has like more, more electronegativity. This is what I believe actually. And this is why we see, also from the, our DFT, it's like, will cover the surface actually. But we are still working on that to understand it in a better way actually. Still we don't have like a solid answer, to be honest with you, for that, but maybe it could be because of the electronegativity, actually, because fluoride can bond much better than iodide on the surface.
Okay, and I can see another one. Thank you for this answer. Gotam, sorry if I missed something in between the presentation, but I have observed the second paper does not consider the first paper result as a control or baseline. Could you help me to get insight?
If he meant because of the efficiency, actually, yes, I agree with him, because you see, because if you see all the three works I presented today, actually, you can see from each work to another work, actually, I'm using like different composition until, I mean, you can see in the last work, I use pure formidinium lead iodide. But in the second work, the composition was completely different, actually. It was not like the same, like triple cation in the, I mean, in the first, like in the first project. If I understand him correctly. But we can see that clearly, actually doing some engineering, we can get back to a much better than, efficiency than like the first work.
Yes, thank you very much for the answer. I cannot see any other question or comment. So I think we can close the presentation here. Thank you very much, Essa. It was very nice, and it was our great pleasure and honor for having you with us.
Thank you so much.
I think we can
And anyone, if he has a question or want to discuss something, I presented my email in the last slide. So
if you can type your email here as well.
Yeah, I will type my email. They can reach me anytime.
Yes, and maybe you can also want to advertise your new positions. Yes, I don't know.
Sorry?
If you
yes,
would like.
Yeah, I'm here. Actually, I just joined CATS at the beginning of the year. I'm working now on large-scale perovskite solar cell. Also, we working, on some other applications, specifically like LED. So we are building here, a very good lab, and also two of my team, attending the course. Their name is Megahead and Barak also. So we are planning to make, to scale up the perovskite, and also we are trying to, do like outdoor tests here in Saudi Arabia. Any idea also is welcome.
Okay, thank you very much. Thanks again for the interesting presentation and all the insights, and for answering all the questions. So now I think we can move to the next one, which is going to be given by myself. So I don't know if Konstantinos would like to introduce myself, but I think it's okay.
No, I can do it. I have to jump to the airport, so that's why I'm on hurry. So let me first switch on the something that will help me a lot. So it's a great pleasure to welcome Dr. George Kakavelakis. Few words about George Kakavelakis. He's a graduate. He has performed his bachelor degree in the Material Science Department of the University of Crete. Then he did his master degree and PhD in third generation and mainly graphene-based third generation solar cells, mainly he has done an excellent work regarding perovskite solar cells and how perovskite solar cells, they can be interfaced with 2D materials regarding the performance, the stability. He moved then to do his postdoctoral fellow in the University of Cambridge under the supervision of Professor Ferrari. They did over there excellent work, and I think as a fruitful result of this work was like a patent, but I don't know if George will mention to us, but it has to do with some innovative carbon-based electrodes that they reduce the thickness a lot, but at the same time they are keeping the electrical properties to the approved standards. He wrote and he won his Marie Curie Fellowship, and he moved to EPFL under the and he nowadays he collaborates with one more famous professor, Professor Michael Gratzel, and he's continuing his work right now, trying to adapt photosynthesis, if I remember well, processes to the solar cells. So George today is going to travel with us through his experience in carbon-based perovskite solar cells and modules. And as I mentioned, George is the main organizer of this school, and the floor is yours. I'm afraid that I have to go to the airport, so I will miss the closing. So you have to moderate the questions.
Okay.
Thank you very much, George, for this.
Okay, maybe I can find someone in the chat, probably Timur or Apostolos. I don't know if they are here, so they can help me with the moderation. I will check this later. So thanks, Konstantinos, for the introduction. So let me share my screen. I guess. You can see my screen. And is it full screen?
Now it is, yes.
Okay, great. So it is a great pleasure and honor to give this talk in the school we organize on perovskite materials and their applications. So this is the outline of my talk. I would like to discuss a bit on energy and climatic crisis, but why solar and solar photovoltaic technologies. But it's very nice that I can somehow skip this and move to the actual point of this presentation, because already Essa and previous speakers already discussed most of these points, but maybe I will try to focus on some things that they didn't mention in their presentation. So yeah, I mean, the energy crisis came up recently due to several unexpected situations that happened in our planet the last few years. And we have seen actually that especially in European Union, we face significant problem regarding an inflation regarding energy, and people are driving crazy, and they are trying to find a way on how to save money or save electricity in this way. And we have seen like almost 40% increase, or even higher, maybe today is maybe 10 times higher than last year compared to the previous prices for natural gas or standard electricity. And then a very important tipping point came to our European Union economy last January, that we have an inflation of around 20 to 30%, around 27% because of energy. So this is a very big problem for a European Union economy. And actually we have seen countries, for example, like Greece, which has more than 40%, or other countries that approach 70% inflation in energy. Of course, the European Union is trying to support with massive funds on how to support the, households on the on how to, let's say, reduce the cost by giving European funds on this topic. And still we are trying to find a way on how to reduce the cost and adopt alternative energy sources. As I mentioned before, we have this crisis, and this crisis is summarized here. So, for example, Greece is the #1 country with the percentage of the GDP compared to, for example, other countries like Ireland or Sweden, that they have only 0.4%. But we have seen, like, for example, countries like Germany and Italy and France, they give massive funds to support their economies regarding the energy crisis. So this is a problem that has to be solved, and maybe alternative energy sources has to be adopted to save this, to solve this problem. Of course, another problem is, of course, the climatic change that is coming on top of the energy crisis, and it is a problem that is going to takes us busy for the next maybe 100 years. And we have seen CO2 levels increased and also temperature levels in our planet increase. Then this is something that cannot be avoided because of the CO2 level rise. And also we have seen some massive change on the climate and the ecosystem of the planet because of this CO2 level problem. And this is something we have to take into consideration and try to change as soon as possible our behavior. There are some policies that try to solve to support this problem on how to maintain the temperature constant, but unfortunately, due to the massive consumption of non-renewable energy sources, this problem is going to continue and give rise to even higher temperatures to the global atmosphere. So, if, for example, we see here that if we cross the line of 1.5 degrees C, the problems start to rise significantly, and it is a high risk of large-scale circular events or global aggregate impacts on our planet. So we have to find a way to reduce this number to less than 2 degrees C for the next 100 years. So we have seen an example of how we can contribute. For example, the pandemic of 2020, coronavirus outbreak, has shown that if we stop, using somehow energies or powering our planet with non-renewable energy sources, this can give rise to significant reduction on some very toxic elements in the Earth's atmosphere. But of course, this is not going to happen so easily. So we have to find a way to change our behavior regarding energy consumption. Unfortunately, this energy demand is going to rise significantly the next 20 to 30 years, and by 2050 it is expected that the global electricity demand will double, and we will have to find a way in doing it in a green way. Today we have seen that around 73% of the energy production is coming from non-renewable energy sources, and only 27% is coming from renewable electricity. So we have to understand why solar photovoltaics is, only 2.8% of this, 2.8% of this pie. Since we always hear, announcement that solar is a very promising technology, is very clean technology, and people are trying to jump on this technology on saving also energy and climate problems. So maybe Essa already presented somehow why solar. Very briefly, it is important to reduce, of course, the carbon footprint. And actually, if you consider that 1 hour of sunshine on the surface of our planet will power the entire planet, if we will be able to exploit this energy. And also solar is abundant, and now it makes also financial meaning to use solar, because solar is much cheaper these days compared to other non-renewable energy sources. And the potential of solar can be seen very clearly in this map, that if we cover these 6 dark spots on this global map with panels of 10% power conversion efficiency, so something that we can easily do even with the renewable third generation photovoltaics, we can solve this problem. Of course, we are not ready to do this because of many limitations of the current technologies, which I'm going to discuss in the next slides. I can skip this part as it is already presented by Essa. This is the global map of the different photovoltaic technologies. It is the crystalline silicon and the emerging PVs. And we are going to focus on the third generation emerging photovoltaics. So I will skip also the principles of energy generation and how it is happening inside the semiconductor materials. And I will focus on this part that all the main materials and panels that are on market currently are based on the first generation photovoltaics, the single crystal or the polycrystalline panels. Then the other technologies, the amorphous silicon, cadmium telluride, and CIGS, as they call the thin film photovoltaics, that because of some issues like the low efficiency or the high toxicity, they didn't manage to get big share of the market. And the last 20 to 30 years, we have the third generation photovoltaics, which promise the lightweight, flexible, high efficiency, and low cost photovoltaic technology. So let's understand why solar is not yet adopted so massively in the energy market. This is mainly because silicon has some drawbacks, and this is mainly because this material is not like an abundant material, so we have to purify silicon to make the solar grade silicon, and this process takes a lot of steps of high temperature and nasty chemicals involved in this process. So it is not straightforward to produce solar grade silicon. And of course, as it was already mentioned before, the technology is not scaled today. So we cannot, let's say, in 1 year produce 20 terawatt power peak of silicon photovoltaic technology because of the abundance and the processes that are not yet scaled to do this kind of job. Another important point that is not considered maybe for solar is that the carbon footprint of solar photovoltaics is not so clean as it is advertised in the news, because of course I explained you already in a few slides ago before that to purify silicon or to make a panel of silicon solar panels requires a lot of waste of energy input actually, and it has actually a lot of nasty materials for the soldering and production of the panel. So in general, it looks, of course, after the production of the panel, the panel is not emitting any CO2, but during production, it involves a lot of CO2 generation for the regarding the energy input. And we can see that regarding alternative energy sources, renewable ones, the silicon solar panels are the less, let's say, environmental friendly. And that's why people around 40 years ago, they started asking this question, if it is possible to find a way to capture sunlight in a more sustainable and high throughput way. And of course, this, I mean, the question has been answered by, let's say, millions or even more years ago by the natural photosynthesis. That is one of the main processes that is happening in our planet to keep the life and make the life sustainable on our planet. And this is, of course, this involves the absorption of sunlight from the leaf or from the leaves of the plants, and this is because of molecular absorption due to the dyes that are inside these leaves of the plants that are called chlorophyll. And this process involves also capture of carbon dioxide, and also then it gives products like oxygen and sugars that is going to feed the plant in order to survive. So this was one of the key, let's say, processes that was the inspiring process on how to make the artificial photosynthesis happen. So let's explore the potential of photosynthesis in order to power our planet. So we have seen that if we do the math correctly and we analyze, let's say, the total energy input and the energy that can be stored in biomass, this is 95 terawatts. If we are able to increase the efficiency of the natural photosynthesis with artificial photosynthesis, we can store up to 95 terawatts of energy in chemical bonds. So this is a very big, inspiration and very big, let's say, motivation for us to work on this technology. And what people have done back in 1992, Michael Gretzer and people from EPFL, they have produced a device that is trying to mimic the natural photosynthesis, using dyes as molecular absorbers to create power in a photovoltaic device. And this is, let's say, the application of this process is called the dye-sensitized solar cell that uses, as I mentioned, the molecular semiconductors to absorb the sunlight, and also it uses colloidal nanoparticles of titanium dioxide that they are able to capture only, to accept only the electrons in this system in order to start the electron flow, in order to create, if we connect this kind of device in an external circuit, it will enable this mesoscopic nanoparticles, the generation and the production of current inside this type of device. Of course, in order to regenerate the dye, people at that time, they invented the use of iodine triiodide electrolyte that is playing the role of the regeneration, playing the role of regenerating the dye in order to avoid the consumption of this kind of material. So what in practice does the electrolyte, it brings back the electron that has been excited and removed from the material. It plays the role of putting back this electron inside the molecular semiconductor. And here you can see, for example, some prototypes of this kind of material. They have also not only the feature of generating electricity, but they are also transparent and they can be made with fancy colors. So it can be used also in other applications such as facades of buildings. And very importantly, what was presented in this work was that by making the materials not like single crystal planar TiO2, by making it in a mesoscopic structure, it was possible to increase let's say the quantum efficiency, or how many electrons can be extracted through in this system compared to how many photons are given to the system. It can be increased by around 1,000 times, and this is because the surface area of the dye has significantly increased because of the let's say 3D system of the titanium dioxide in this mesoscopic film. So another very important contribution on this topic was the development of the solid-state DSC, so trying to replace now the DSC's electrolyte from the liquid to a solid state. And this was presented back in 1998 by people from EPFL again, and they used a material that is currently also used in the modern photovoltaics, the perovskite ones. It's called spirometad, or analogous to spiro materials, as a solid state material in order to make the first solid state DSC. And as it was already presented by Essa before, other people tried to invent new dyes, and Professor Miyasaka and people from Japan, they managed to produce the modern dyes, or let's say the halide perovskite materials, in order to work as a dye in a solar cell. So all these type of materials have already presented before, halide perovskites. So they have this ABX3 cubic structure with lead iodide octahedra. So typical elements that can be put are methylammonium orthomamidinium, iodide, bromide, or chloride at the corner. So this octahedra, and in the middle, it can be used lead or tin. So and combining, let's say, these two worlds of the solid state DSE and the halide perovskites, people they managed to make the first highly efficient perovskite solar cells utilizing the mesoscopic structure back in 2012. I can skip this part as it is already presented, and I can briefly say that this type of materials, they are so promising semiconductors because they combine both the inorganic and organic worlds, so they can be solution processed. We can easily tune their band gap by changing the composition as it has been presented before, and also they have very strong absorption coefficient in long energetic disorders. I can skip this part, and I can briefly mention that one of the big benefits about the perovskite solar cell is that this type of systems can be deposited by using different printing techniques. So in comparison to the high temperature method, vapor and high temperature depositions of other materials, this type of materials can be printed actually at room temperature using this type of techniques like blade coating, slot die, inkjet printing, or spray coating to make this type of films or this type of devices actually at a low temperature with printing, utilizing printing techniques. Yeah. So very briefly, as I already mentioned, the devices in this type of systems like the perovskite solar cells can be fabricated either as it is already presented in the mesoscopic structure, so we use the titanium dioxide mesoporous film, or even it has been shown that we can remove this type of material and put it in a planar configuration, having the electron transport layer and the whole transport layers sandwiched between the perovskite materials. I can skip this part as is already presented. And the very typical operating principle of this type of device is that we have a transparent conductor, an electron transporting layer, the absorber layer that is the perovskite, and a p-type material, and a back electrode, a reflective electrode. And how this device works, actually the incident light is passing through the front contact, which should be transparent. So FTO stands for fluorinated tin oxide, and titanium dioxide is the N-type contact. So the light has to reach the absorber material. The electron is excited from the ground state to the excited state, and then because of this electron selective layer and hole selective layer, the respective charges are collected at the respective electrodes, and then the power is generated because of the voltage that is created at the N and the P side contact of this type of system, and of course the current that is generated due to the flow of the electron inside this device. So there is a plethora of materials that can be used on this type of device, such as inorganic or organic N-type materials for electron transporting layers, and also many different P-type layers, both inorganic, such as copper thiocyanate, nickel oxide, or organic whole transporting layers, such as the most commonly used, actually, pyrometal. But as you can see here, there are only a few options for the metal electrode and also the transparent electrode. And I will come to this point later in my presentation. So as it has been already presented, we have already seen efficiencies of more than 25%. And actually, this work, for example, was presented last year from Dr. Jackie Jeong from EPFL, from our lab, and he managed to achieve certified performances of above 25%. And in the lab, actually more than 25.7. And we have seen that using this type of system that actually is very similar to a solid state DSC. So everything started actually from the solid state DSC. As you can see here, for example, we still use spirometat as a solid state HTM. Still, we have the mesoscopic TiO2, but we have some new materials like perovskites and octylammonium iodide, as it was presented before, as the absorber layer and the passivation layer. And we have seen some fantastic results of more than 25% using this system. But as you can see here, this type of device utilizes gold as the collecting electrode. And also from our group and in collaboration with the Korean group, researchers from our lab have managed to achieve efficiencies this time of 25.4% certified by an external accredited institute, using in this time replacing the mesoporous TiO2 with quantum dot tin oxide on top of a compact TiO2 electron selective layer. So we have seen that now the field is moving to a, let's say, planar configuration instead of the meso configuration in order to push the efficiency to even higher values. And actually also we have seen recently for the inverted configuration, which is very promising for the tandems, we have seen that it can be also realized in this configuration. It can be realized highly efficient perovskite solar cells, recently achieving 24% or higher, combined with very high operational stabilities using the standard protocol, the down heat test at 85 degrees C, 85% relative humidity. And these results are actually very promising for commercialization. And also other promising results demonstrating even more than 24, close to 25% power conversion efficiency. But as it has been presented before, this type of device utilizes gold, and gold, we already know it is a very expensive material. And also it has some issues combined with the dopants that are used inside the Hall selective layer, the spirometat. They start to make problems regarding also the stability of the system, and I will explain this in a minute. So, and another, of course, very important problem is that to evaporate gold films on top of this solution process photovoltaic device requires an energy input due to high temperature processing and ultra high vacuum. And as I explained also, in combination with the dopants that are used inside the spirometat, and this is like some hygroscopic materials such as lithium, TFSI or TLP, this type of system, the whole selective layer and gold and perovskite interface, it's very unstable, and it has been, let's say, reported some years ago that when this type of interface and device is exposed at high temperature, this interface and especially the gold tends to migrate inside the perovskite, and it is doing some gold-induced degradation inside the perovskite film. So a possible solution to this problem is to transition and let's say replace these expensive and problematic materials, both spiro and gold, of the typical perovskite solar cells that give the very high, of course, efficiencies, more than 25% already certified, and transition to a cheap and high throughput current collectors. So we have to go back again many years actually and see that it has been already presented by people at TPFL and especially Professor Gratzel, that it is possible to replace even in a DSC, in a disolar cell, device, let's say the electrode in this case was actually a platinum electrode based on deposited on top of FTO that is playing the role of the catalyst. Here it can be replaced by carbon powder, as it has been reported in this publication back in 1996. And actually they presented for the first time a device that can be actually let's say put in a pilot line and roll-to-roll fabricated fully on top of this type of system using a carbon paste instead of a typical metallic electrode. So we have seen then a transition from a typical let's say photovoltaic device that is either mesoscopic or planar, using this type of materials that, as I presented, are expensive and they cause some degradation issues. We have seen recently in the literature that a transition to a fully printed perovskite solar cell utilizing carbon as the material to replace the metal electrode, and sometimes even for, especially in this type of configuration, to replace even the HTM, making an HTM-free device or having some inorganic HTMs like nickel oxide. So this first configuration is called the mesoscopic one because actually the titanium dioxide, zirconium oxide, mesoporous HTM and carbon electrode are first deposited on top of a compact titanium dioxide covered, sorry, I have to admit also people at the same time. So on top of a FTO glass substrate, and then the perovskite solution is infiltrated through the pores of this electrode. And this type of device is called the mesoscopic perovskite solar cell. But also it is possible actually to replace completely the metal electrode and deposit it on top of the HTM or on top of the perovskite, and actually in this case just replace the metal electrode with a carbon electrode. In this configuration, it is called the paintable carbon-based perovskite solar cell. So I will demonstrate to you a few key results of both the mesoscopic and the paintable device configuration. I can skip this part and go directly to the first actually fully printed carbon-based perovskite solar cell that was actually presented 2013. And in this work, as you can see in the abstract, actually people, they used a carbon-based counter electrode. At that time it was carbon black and doped with some spheroidal graphite, and they utilized this mesoscopic based configuration. And the main point of this system is that, as I mentioned before, it can be even actually HTM free, so we can both save, let's say, the cost of this in this kind of device regarding the electrode, but also the HTM. And in this case, people have managed to achieve very low power conversion efficiency, and I will explain to you in a minute why this type of system was very low, because the conductivity of this type of electrode, the counter electrode based on carbon black and spheroidal graphite, had very low conductivity, and they didn't manage to get very high power conversion efficiency because of this reason. And later on, next year, to 2014, people from China, they managed to replace the spheroidal graphite with standard graphite flakes, and by also changing actually the configuration of the perovskite material and the perovskite infiltration through the porous, they managed to improve the efficiency of this type of system to almost double values, around 11.2%, which was a very promising result, mainly especially because of the stability, because at that time the stability of the perovskite solar cells were very low. So in this work, the people managed to reach more than 1,000 hours of stability with efficiency of more than 10% power conversion efficiency. And actually, a few years later, Giulia Gansini and co-workers also presented the first one-year stable perovskite solar cell, which was a very big breakthrough at that time, utilizing actually a 2D, 3D passivation system for the perovskite solar cell, combined with some additives inside the perovskite material AVAI. And they managed to achieve also very highly efficient solar modules based on this type of configuration and having power conversion efficiency of more than 10% in this figure of merit. So they have been already presented that this type of configuration, the mesoscopic TiO2 zirconia and mesoscopic carbon, is a very promising technology in order to reach, as you have seen, a very highly stable device and also a very, let's say, highly efficient, or at least at that time, solar modules, which is very important to demonstrate also for the commercialization of this technology. And also, actually, based on this type of configuration, people from China, they managed to make also the first solar array of panels. So they presented how to make a panel of 96 of this type of modules that you see here, and they connected these panels in order to make the first ever presented perovskite solar array of panels in the world. And as you can see here, with very stable power conversion efficiency, but actually with very low power conversion efficiency at the same time, so around 8% in real operative conditions. So the conclusion, let's say, for this type of system is that it can be a very stable and very reliable method for this mesoscopic system on how to make the solar cells, but the power conversion efficiency cannot exceed and cannot, let's say, go closer to the standard gold-based devices. So then the other configuration came to the game, as I mentioned, as it is called the paintable based configuration. And in this case, what actually the researchers do is they somehow print, let's say, the carbon electrode on top of the HTM or any interfacial layer or on the perovskite, and we don't need to change completely the configuration of this type of system, such as, for example, in the other case that we have to deposit mesoporous TiO2, mesoporous zirconia, and mesoporous carbon. No, in this case, we just replace the electrode with a carbon-based system. And actually, in this work, what people have done, they have done something really important for the field. They have used different solvents in order to understand which solvent is compatible with different HTMs and different perovskites. And they have presented that, for example, chloroform or toluene are very promising solvents because of the low boiling point. So, of course, we know from the previous speakers that the perovskite material cannot sustain high temperature, so we have to find a boiling point for our solvent that is not exceeding, let's say, 150 degrees. So we can see that toluene is a promising solvent, and maybe chloroform has some potential, but because it has very low boiling point, maybe the stability of the paste cannot be very let's say, extended. So we have to find a balance on these 2 points. And of course, what people have done, they have used, I think, toluene in this work, and they have used 2 different systems, P3HT and CuSEN, that it is a material that we have already presented in our group, that it is very promising in perovskite solar cells. They have managed to achieve some very important increase in power conversion efficiency, and also demonstrate again the superiority of this system compared to any. So, for example, in this case, they used silver as a reference. They have demonstrated the superiority of the carbon-based electrodes, especially for the stability, because we don't have anymore this problem of the metal diffusion inside the perovskite film. And also some more advanced characterization have shown that actually by putting some interlayers in this kind of system, you can even improve even further the stability of your device. And also a few years ago, 2019, people from our group here at EPFL, they also demonstrated some very interesting results on this topic by using again this type of configuration and putting some advanced carbon-based electrodes, mainly based on graphite, and using copper thiocyanate, that it is a material, it seems it has been demonstrated very promising results, but the point is it has some trick deposition procedures that has to be adopted in order to make it compatible with the perovskite fabrication methods. So what these people from EPFL have shown in this publication is that they have managed to achieve and boost the efficiency of the perovskite solar cell to more than 15% using a 17% bromide system. And even actually, most importantly, they have shown that if you switch to a less bromide system, they have managed to boost the efficiency to more than 18% and achieve fill factors of more than 76%. So this is something really promising results, because both copper thiocyanate and carbon satisfy what we discussed in the beginning of my talk, very low cost and very stable materials. Of course, I mean, one have to demonstrate the scalability of this system. And this is also very important because this type of system is also very stable, and people have presented extended stability at 1 sun illumination and also UV exposure for more than 1,000 hours. And another very promising result also came from another group in Germany in collaboration with EPFL. They also demonstrated that you can even remove the HTM and putting octylammonium iodide, which is actually a passivation layer for the standard perovskite solar cell. Actually, you can create some favorable interface blocking, let's say, the electron recombination at the perovskite carbon interface. So in this case, actually, the 2D perovskite, the octylammonium iodide, plays the role of, let's say, the whole, the electron blocking layer, facilitating at the same time the whole extraction at the perovskite 2D perovskite or OAI, perovskite OAI interface, and they managed to achieve also in this case some very promising results on how to achieve very high efficiency perovskite cells, and some very promising results regarding stability, achieving 80%, retaining 80% of the lifetime after 500 hours. So it seems that actually this interface between the perovskite and the carbon electrode plays some very important role, both when you use 2D perovskite or when you use some of the typical or some of the advanced whole conductors in this system. And actually, what was very important, they also demonstrated that if one can improve this interface and use some very highly conductive carbon electrodes, one can improve the fill factor of this system, which is the main, let's say, limitation on how to achieve high efficiency, is using, let's say, optimized interface and also some highly conductive carbon electrodes. One can achieve even more than 80 or even 86% fill factor for this type of system. So this is very important result, but only theoretically presented in this very interesting work. So as I have presented, and in the last 10 minutes of my work, of my presentation, I will present you actually what I have done the recent years. So as I presented you already, and I would like now to give you some numbers as well. The main problem on the field is also coming from the carbon electrode. It's not only the interface between the perovskite and the carbon film, but it is also the carbon film itself, because even this breakthrough on putting some additives of graphite powder inside the carbon, the carbon black, and as you can see here, this is some optimized compositions. So, for example, 50% of graphite inside the carbon black is a very promising approach to reduce, let's say, the heat resistance of this type of system. But still, as you probably already know, let's say a thin film of a gold layer of around 50 to 100 nanometers will have less than one, around maybe 0.1 ohm per square heat resistance. So we can see that we already have 100 times higher heat resistance at this collecting electrode. So and up to now, all the typical heat resistant, all the typical carbon-based films has heat resistance of more than 10 ohm per square. So actually, this was a very big driving force for myself to study and investigate these carbon-based materials. And actually, we during my work at Cambridge University, we focused on graphene and how we can integrate graphene in the perovskite solar cell as an alternative material for metallic electrodes and also for the typical carbon-based electrodes. And why graphene? Because graphene have some very promising properties regarding electrical conductivity and how you can process this type of material to make it as a conductive paste. So we have selected to work on this type of system. Of course, a few words about graphene. Graphene is carbon allotrope, and actually it can be very easily prepared if one can exfoliate graphite. But of course, this is not a very easy method to do. Actually, what was done initially for the Nobel Prize, the people used the Scotch tape method, which is actually a method that is very, let's say, efficient on how to exfoliate graphite, but you cannot scale up this method to make any practical application. So people then tried to invent an alternative methods such as CVD or solution processing. And in order to, let's say, match the need for fully printed photovoltaics, we decided to focus on liquid exfoliation. And we have invented a method that is currently patented in order to exfoliate graphite and formulate graphene-based pastes with a method that is called high-pressure homogenization of graphite. But this method actually can be adopted to any type of layered material in order to exfoliate, for example, other types of systems such as boron nitride or TMDs. And why was this important? Because with this method, it is possible to tune the properties and to fine-tune the morphology of the system, because as you have seen before in the previous slides, the morphology of the flakes plays very important role, and the diameter of the flakes plays very important role in order to make a very compact system. very compact film and very compact interface with the perovskite or the HTM. So we can even not only, let's say, improve conductivities, but also we can tune, let's say, the morphological characteristics of the flakes. And according to the application, for example, if you want to use a mesoscopic system, such as like energy storage device, you can use a certain number of exfoliation cycles, or if you want to use some other application that requires very compact film, you can process the material further. So we have done this method, and we have managed to tune or to reduce the heat resistance of this kind of material even less than 3 ohm per square, which is a very big breakthrough for carbon-based electrodes. And actually, we have even now managed to further reduce this kind of electrodes heat resistance by doing some modification on the precursor material that we are trying now to patent as well. And we have managed, by using this type of system, a mesoporous, TiO2-based perovskite solar cell combined with organic hole transporting layers, we have managed to see that this exfoliation process is very effective, and at a certain time, at a certain number of cycles of exfoliation, we can improve the efficiency of our solar cells to even close to 15%, even though this type of device is not fully optimized regarding the perovskite composition. Even we have seen that it can be improved by switching to more efficient electron selective contacts or hole selective contacts. But another very important point is that we have also done some interesting characterization regarding the age of the paste and how this aged paste can be also used in a solar cell. We have seen that the heat resistance does not change almost at all, and also the device performance almost is the same for a fresh or aged paste. And we have also seen some interesting results regarding stability using typical ISOs D1 and D2 protocols, surpassing 1000 hours with less than 5% of efficiency loss. So why is this important? Because, I mean, as I explained before, this is important regarding cost and scalability, and people from China, they have presented that if one can obtain 15 years of lifetime combined with 15% power conversion efficiency on a module level, this can yield a levelized cost of electricity, or let's say the cost per kilowatt hour of less than 5 cents of US dollar, which is a very, very low value comparing to even the standard photovoltaics, and of course imagining comparing with a standard means of producing electricity. And of course our target, since we have already achieved this 15 power conversion efficiency, is to target even pushing the efficiency to 20%, which will enable a very low value of less than $4 per US dollars per kilowatt hour. And of course, as I mentioned, if this can be done on a module or on a panel size, this will enable, let's say, the perovskite solar cells to be the lowest technology regarding LCOE, the lowest value technology for LCOE regarding any energy generation technology. So this, we believe that we will unlock the potential of this technology, and in general will boost the photovoltaic devices application and massive market sharing. I still have 2 minutes. I have actually presented, I would like also to present you some things regarding the transparent electrode, and of course, because of limitation, I will not be able to do it here. But since I mean, as I presented you before in the last presentation, today's presentation, it was already cancelled by the speaker. I will probably discuss with you regarding the cost, especially of the cost distribution, and then I will analyze how the perovskite, the fully printed perovskite solar cells can be a very good option. And then I will discuss also about the TCO, that is for this type of technology, is the main cost regarding this type of device. So I will now jump directly to the end of my presentation, and I will try to conclude in the rest 1 minute I still have until the end of my talk. So combined with Issa's lecture, I presented you the importance of solar and how this technology can solve climate and energy crisis. Then, of course, I presented you that new materials and PV technologies are needed to improve the figure of merits, and especially the cost competitiveness and scalability of the solar panels. Solution process photovoltaic looks very promising technology. And of course, even for this type of technology, there are several issues that need to be resolved. I discussed already the HTM and the gold electrodes, that mainly they are utilized in this type of systems for the highly efficient solar cells, the NIP ones, even of course for the PIN ones that they don't use gold, but they use silver. Maybe the cost is much lower, but still the degradation because of iodide, silver iodide, let's say perovskite degradation is happening. Still, we have to use alternative to metal electrodes in order to improve the figure of merit of this technology. And also, I tried to explain you the importance of carbon-based materials, especially in order to replace the metal electrodes, and the use, of course, of graphene and how important it is in order to further improve the efficiency of carbon-based devices, or mainly improve the stability and also reduce the cost of this type of systems. So I would like, of course, to thank my funding from Marie Sklodowska-Curie Actions and this individual fellowship from European Commission's Horizon Europe Fund with this grant agreement. And of course, I would like to thank you for your attention, your kind attention, and I would like to give the floor to the audience for any questions. So let me stop sharing, and probably maybe I can ask Essa to help me with moderating if still Essa is in the call. Are you here? Or Timur? Maybe I can ask Timur.
Hello, George.
Hello. So
Can you hear me?
Yes, please. Can you go through the chat?
Maybe
Yes.
I can help you moderate the questions.
Thank you.
Okay, so first question is from the chat from Apostolos Panagitopoulos. Thank you, George, for a very interesting presentation and your point of view regarding the potential of use of carbon electrodes. How do they compete compared to other counterparts in large area modules, PVs? And how about their implementation to other emerging technologies, OPVs, for example?
Thank you very much, Apostolos, for the interesting question. How do they compete to other counterparts? As I explained, at least for the small area up to date, and even for the large area to some extent, the main benefit is on how we can make these devices stable, because this type of systems, carbon materials, are very inert and they don't react with, let's say, other materials or systems. So in this case, we can solve, let's say, the instability because of this metal electrode and perovskite interface that is mainly caused when we use hydroscopic materials. Another very important point, of course, is the scalability, because this type of system has solution process. So we don't have to put our cells or modules inside an evaporator. And if you are familiar with photovoltaics, the throughput of a module or a panel, or of the module at least, is very important regarding the cost. So if you can avoid inserting your modules inside a thermal evaporator that has to go through high temperature and high vacuum deposition means, it will be very important for the implementation and the, let's say, commercial competence of this type of systems. And then the other important thing, of course, is the cost, because if we want to use, for example, this type of technology, we have to get rid of the metals, and especially gold is a no-go for commercializing this technology. Imagine that if we use gold, only the gold itself in a solar panel, it will be twice the amount of a typical silicon solar panel, only gold. So we have to get rid of this type of material. And if we want to discuss about large area, of course, since this type of materials are printable, we can use any printable technique in order to print this type of material at low temperature, and even using the typical methods for deposition, such as blade or screen printing, we can print large area electrodes very fast and with very high precision. About implementation to other PV technologies, of course, we have seen very promising results on DSEs, because it has been already presented that carbon-based materials are very promising to replace the metal catalysts or polymer catalysts in the dye-sensitized solar cell. Now, regarding the organic photovoltaics, this I mean has to be checked. I'm not very familiar. Of course, carbon-based materials and especially conductive polymers have been already used as printable electrodes, but I'm not pretty sure what about the materials that we exploit in my case. I think I covered the question of Apostolos, so I think, Timur, you can...
Hello, can you hear me? Okay, now I'm muted. So next question is coming from Mahin. Amazing presentation. I would like to know how adhesion of carbon or graphene is provided with whole transport material underneath. And another use of carbon may increase carbon footprint as well, besides decreasing cost in comparison to gold electrode.
Of course, there are tricks. We can process graphene and attach some, for example, functionalities, or we can process the surface of the HTM or perovskite in order to make, let's say, the surface of the perovskite or the HTM respectively more favorable for the adhesion of the graphene or any other carbon electrode. So, of course, binders play a very important role in this type of system, and modifiers of the surface. So another way, let's say, to bypass any potential problem, if there is any, is to treat graphite flakes itself and attach some functionalities in order to make the adhesion to this type of surfaces, both perovskite or any type of HTM, possible. So this is a beauty of carbon-based materials, and especially graphite. It has very high degree of flexibility in attaching different groups, in modifying the surface, or let's say putting some additives to improve adhesion of this type of materials. Now, the second question was...
And then I think the second question
may increase carbon footprint. I don't agree too much with you, because imagine that this type of systems can be solution processed and can be deposited at room temperature. Of course, one has to think about the source of the carbon. But if we use, for example, natural graphite, or we find a way to synthesize graphite, and I'm giving you a hint now, to synthesize graphite in a more sustainable way, because it is possible to have synthetic graphite, and then formulate these inks that I presented, make the ink using, let's say, low consumption or low carbon footprint techniques. And then apply these inks to the devices at low temperature with room temperature deposition means actually the carbon footprint, and we have done some calculation recently, the carbon footprint using this type of system can be orders of magnitude lower than any other material that is used in any photovoltaic technology, not only perovskite, but in any photovoltaic technology. I think I covered this one, so.
Thank you, George. Maybe we can move to the next question.
Yes.
So the next one is, dear George, thank you for the very interesting presentation. Have you considered to use conductive linkers between the graphene sheets? It has been shown that they give a concurrent effectiveness in conductivity and mechanical property as well.
Conductive linker. I don't know if maybe we can ask C. Pavlu to unmute. Actually, I have to ask him, C. Pavlu. Maybe if C. Pavlu would like, I will ask you now to unmute and explain me exactly what do you mean by conductive linkers.
Hello.
Hello.
Hello, I'm Christos. Thanks for the very interesting presentation.
Thank you, Christos.
Actually, I was trying to say briefly that to use molecules that actually are conductive, such as polydopamine, that it has been done as an extensive research by Professor Baumann, that actually it connects the two flakes between, makes a connection between two flakes, which actually works also, it actually promotes the fast electron transport, and also it makes a stable connection between the graphene sheets. So it has shown that it gives effectiveness in terms of mechanical properties and conductivity as well.
Thank you very much for this, comment or in question. Actually, to be honest with you, we haven't considered so far making this, let's say, modification in our graphene system or graphene paste, since we have seen that the morphology of the flakes plays a very important role, at least to achieve very low sheet resistance so far. But maybe I will keep an eye, and if you want, you can drop me an email and we can discuss it further.
Yes.
On how maybe we can collaborate on going, let's say, towards this direction in the future. Why not?
Okay, we can discuss it.
Yes.
Pleasure.
Okay, but as I explained in the presentation, at least in our case, morphology seems to be at least up to now. Maybe what you suggested maybe can be a very big breakthrough, but morphology seems to be the most important method in how to go from tens of ohms per square to even very close to 1 ohm per square. But thank you very much for the question. I will type here my email, so maybe you can send me an email and we can discuss it further.
Okay. I will be very glad.
Thank you very much.
My
So Timur, maybe we can move.
George. Yes, maybe we can move to next question.
We
From
have
Clara.
3 minutes.
Yeah. Thank you. How low sheet resistance do you think is needed for carbon electrodes to be okay? What do you think is the upper limit for resistant losses?
So yes, thank you very much for the question. Very interesting. Actually, this is what we also. It was a very big puzzle in the beginning, because actually there is no, let's say, guideline on what to do. But if you consider, of course, that in the typical perovskite solar cell that uses metallic electrodes that have, for example, in gold case, less than 1 ohm per square seat resistance, the limiting factor in this kind of device, one of the limiting factors, at least when you are going to large area, is the resistivity of the transparent electrode, and this is what I will discuss in the second part of my presentation after lunch. Is, as you probably already know, this the FTO, the fluorine doped-in oxide or indium tin oxide, which has around 7 to 15 ohm per square. So what I believe is, if you can manage to reduce the seat resistance of your electrode, of your conductive electrode, to less than this, you are good to go and make a very good device. Of course, it is not only the seat resistance that plays an important role, but also the morphology, because current collection, the carriers can be scattered, so you can lose carriers when the surface is not very flat, or if the surface is very thick. Another important point is if you can thin down your electrode but still maintain the very low seat resistance. So I think the values that we have reached, this 3 to 5 ohm per square, should be enough in order not the seat resistance of the carbon electrode to limit the performance of our perovskite solar cells. Then if we go to modules, or even when scaling up, maybe we will have to reconsider this, let's say, threshold limits.
Thanks, George. And maybe you can let me know if we have some time, because there are 3 more questions.
I think now, let me check. I think now we have the, let me check.
Otherwise, people from chat can address the questions through email with you, or maybe in the chat box.
Now we have the coffee break, so we can, let's say, still few minutes. I'm happy to address the comments, and if people they want to go for a coffee break, they can go, and I will keep replying to the questions as it is recorded, so they can check my replies later on.
So maybe you can move to the next question.
Yes.
Okay, next question is coming from Priyanka. Dear George, thanks for this wonderful presentation. I have a theory regarding question, I believe, regarding graphene ink, that a graphene or some alternative GO, RGO was utilized for ink preparation, because pure graphene itself is still costlier material. And second part of the question is, please also comment about the stability of the ink time, because after some time graphene will settle down. How they are maintained in dispersed form in ink?
Thank you, Priyanka, for this interesting question. So in the method that is actually patented during my work in Cambridge University, we have found a way to use actually graphite, not modified graphite such as graphite oxide or reduced graphite oxide and this type of materials. We used graphite, and in this case we were able, by this exfoliation method that I presented you before, we were able to make this type of inks based on exfoliated graphite and not graphene oxide or reduced graphene oxide. And at the same time, we used these graphene nanoplatelets that are produced after the processing of the material. Let me also admit some people to enter the call. We use this material and we managed to make it scalable and cost effective. So at the same time, we are using, of course, it is not a single layer graphene, which is indeed very expensive. It is graphene nanoplatelets or graphite nanoplatelets with very thin, let's say, with very low thickness regarding the flake property. So we, just a moment. So we managed with this type of method that we demonstrated before to make inks based on graphite, exfoliated graphite, and at the same time very cost effective. Mainly because of the low, let's say, value, low price of the precursor material, and also the scalability and the high throughput of our method. Now going to the second part of this question. So of course, these materials are especially engineered by different means, both at the exfoliation procedure and additives, in order to avoid the sedimentation of the flakes and also agglomeration of the flakes. So we have done, but unfortunately I cannot discuss at that point. At this point, this question or this let's say comment of the pre-Yanka, because we have some disclosure currently agreement. So I can say that this material, as I presented in my presentation, we have done some aging tests, and after even 1 year or more, the material itself is stable, and when you're going to make a device out of it, the device performance will be more or less the same as when it is freshly prepared.
Thanks, George. Maybe we can move to the next question. Dear George, thank you for the helpful presentation. For this kind of carbon, which are patent and it's confidential, but still kind of carbon are commercially available? I'm not sure if I understand the
Which
question.
are, maybe this is a comment, not a question. I think this is a comment.
Okay, maybe then we can move to
We
the
can
next
move to the
question.
next one.
Thank you, George, for a very interesting presentation. As you mentioned that ITO and FTO are only options for transparent conductive oxide layer. Do you have any comments on this? Also, does the post-treatment process for layers after deposition have any other roles? Other roles than removing solvents?
So let me keep these ITO, FTO points for the second part of my presentation. But of course, I would say that people, they don't mention, but indium tin oxide is a very toxic material. It contains indium. So, but we have seen that people complain about the toxicity of the perovskite, but not about the indium tin oxide. So I think that the only way to go is with FTO, but of course, with FTO, we have some other limitations because we have to use thicker glass, so the transparency is lower, and especially when we go to longer wavelengths, FTO absorbs a lot. So when we consider, tandem devices, it will be an issue. So let me give you in my second presentation after lunch all the information regarding how, or at least some hints on how we can somehow try to replace this type of materials with carbon-based materials again. And the other point was regarding this portion. I'm not really sure in which step you mean, Navin, in which step you mean post-treatment for layers? Of course, I don't know if you mean regarding anti-solvent quenching of the perovskite. Of course, this is mainly to remove, solvent during the growth in order to control crystallization. But other than this, I'm not sure which post-treatment you mean.
George, I think the person commented on this. He means
Ah.
for all the active layers, EPL, HTL, and perovskite.
Okay, so
I believe the thermal annealing process is that he's meaning. He wants to say.
maybe. So especially regarding, of course, the electron selective contact, which is, for example, mesoporous titanium dioxide, we have to do the post-treatment in order to create this three-dimensional junction, three-dimensional porous network. But in the case, for example, of using Jakey's method, when we have the compact, tin oxide, for example, the nanoparticles already are in the crystalline form, so we don't need to do the thermal treatment in order to, for example, make the nanoparticles more oriented or more crystalline, but this is mainly to remove solvents. Regarding HTL, normally we don't use thermal treatment because it is normally deposited on top of perovskite, and we want to avoid the, thermal treatment when we have already deposited and fabricated our perovskite. And in the case of perovskite, it is for providing, let's say, the energy in order to start the crystallization process and make the perovskite from the non-perovskite, the perovskite precursor film from this non-perovskite phase to the perovskite phase. Yeah, I think that's it. And I also had one question from I cannot find it now in my direct message, but I cannot find it right now. So I think we can end this session. So everybody, I would like to thank everybody for attending the morning session, and also for listening to our talks. It was a great pleasure to have Essa ALHARBI in the morning session, and it was very nice for me giving this presentation for you regarding a very important topic and my work, actually. So let's meet in around 20 minutes for the next talk, which will be given by Dr. Mingyang on the high-efficiency all-perovskite tandem cells. Thank you very much. So welcome again to the after coffee break session for our second day's lectures on the intensive course on metal halide perovskites from materials to applications. And so this second day is devoted to energy harvesting devices. And it's a great pleasure and honor to have in this slot today with us Dr. Mingyang from EPFL in Switzerland. So Mingyang is a postdoctoral researcher at EPFL in Lausanne. He received his bachelor degree in physics from the Peking University in 2016, followed by a PhD at the University of Toronto in 2020 under the supervision of Professor Ted Sargent. So Mingyang is an expert on the synthesis of photophysical understanding on metal halide perovskites towards a better single junction and tandem solar cells, luminescent solar concentrators, and optical communicators. He has received over 5,000 citations, and he has an index of over 30. And he is also actually a Marie Sklodowska-Curie individual fellow at EPFL, and he is Canada's Governor General's gold medal receiver. So it is a great pleasure, Mingyang, to have you as our lecturer today. So please share your screen and start your presentation. And it could be great if you can open your camera as well. If not, it's okay. Okay,
Yeah.
good. Thank you.
Yeah. So thanks, George, for your invitation and also introduction. It's my great pleasure to join today's lecture. And what I'm going to talking about is all-perovskite tandem solar cells, something closely related to my own research. So as already George introduced, I'm a postdoc fellow in EPFL and working with Professor Michael Grazo. And also I'm a colleague of George. So in today's presentation, I will introduce the concept of tandem photovoltaics and how we use perovskite materials to demonstrate tandem solar cells. So this will include the recent progress on device efficiencies, which is our work at University of Toronto, and also their challenges in stability and scalability. So this is a newborn field and it's fast growing and has a lot of research challenges. And eventually is a conclusion and outlook. So as we all know that the solar energy is really fast growing in the recent decade. Solar and wind are becoming increasingly cheap, and together they are accounting for over 0.5% of the new energy installations worldwide. So it's a growing field and has a lot of exciting opportunities. The current development of this renewable energy is largely driven by the continuous cost reduction of silicon solar cells. In the past decade, we see greatly reduced costs for silicon solar cells because of their rapid learning and also economy of scales. We see big factories set up in China to continuously produce silicon modules in very large scale. So, but the question is how we can continue this trend, how we can continue to reduce the cost of silicon, of solar cells in general. This means we need to develop next generation technologies with higher power conversion efficiency and even lower cost. Sorry. So before we introduce tandem concept, let's talk about the efficiency limit of single junction solar cells. As you already know that a solar cell is fundamentally composed of semiconductor material that can absorb sunlight and convert it to electricity. So let's focus on what happens within a single junction semiconductor when it absorbs sunlight. Solar radiation is a continuous radiation. It contains a lot of different photon energies. So for a semiconductor with a certain band gap of, let's say, Eg, for photon energy that below that this band gap is not absorbed. So it attributes to some optical losses in this process. And the solar radiation also contains high energy photons. These photons are absorbed by semiconductors, but because it's high energy photons, it generates electron holes will quickly relax to the band edge state. So during this relaxation process, it generates a lot of heat, which also wasted, not used. So it's called thermalization loss. And after it generates electron holes, it will recombine. This is recombination loss. So combining all these losses, we have this efficiency limit for single junction solar cells with a certain band gap. You can see silicon is here. Silicon has a band gap of 1.1 eV. Its efficiency limit is around 32%. And currently, it's, the efficient record for silicon is 26 or 27%. And there are other technologies that are all below this limit. And perovskite is 25.7. It's a very efficient technology for single junction, but their efficiency limit is around 30%. So our motivation is to develop this tandem is to try to break this efficiency limit using this new technology. So why tandem solar cell can increase the efficiency limit? Tandem solar cell in general compose of two subcells with two different bandgap semiconductors. So you can see here, there's a wide bandgap semiconductor in the front and a lower bandgap semiconductor in the bottom. So when it absorbs solar irradiation, previously this low energy photon, which cannot be collected by the wide bandgap top cell, it can be absorbed by the bottom cell right now to generate photocurrent. And these high energy photons absorbed by the top cell, because this top cell has a very large bandgap, so it wouldn't contribute to thermalization loss. Instead, it can generate very high photovoltage. So it doesn't, so it can reduce this thermalization loss. So you can see it's a strategy that can absorb low energy photons and reduce thermalization loss from high energy photons. So it can reduce the efficiency loss to generate higher theoretical efficiency. So here is a figure showing that what's the theoretical efficiency you can get from a tandem solar cell. So you can see the top cell and bottom cell have different band gaps. Under certain band gap, it has a maximum power conversion efficiency, which is for this configuration, let's see, 1.8 EV top cell band gap, 1.2 EV bottom cell band gap, it can generate 42%. And as a reminder, silicon has the 32% efficiency limit. So it's a 10% increase. It's a huge number in photovoltaics. That's why people are highly motivated to demonstrate tandem solar cell using different photovoltaic materials. How do we achieve this tandem concept in real devices? So here I introduce these two types of tandem configurations in solar cells. So the first one is called 2T tandem. A 2D tandem combines this bottom cell and top cell. In the middle, it has this recombination layer. It is usually a transparent oxide layer that can recombine electron holes. So sunlight comes from bottom, and this high energy photons are first absorbed by the top cell, and low energy photons are absorbed by the bottom cell. And both of them generate photocurrent, come from these two sides. And in the middle, this electron holes come from the top and bottom are recombined here. So you can see that this type of configuration combine two subcells into one tandem cell, and so basically these two subcells are connected in series. And the right side is 4T tandem. So instead of combine two subcells, this 4T tandem, these two subcells are operated independently. So you can see that when light comes through here, first high energy photons are absorbed by the top cell, and it will generate photocurrent on these two sides. And then the low energy photons will absorb by this bottom cell. It also generates photocurrent on these two sides. So these two cells are operated independently. So how make, we know that in single junction solar cells, it has this gold or metal electrode that is overcut and cannot be transparent. So how can you make sure this bottom cell can also absorb solar radiation to generate photocurrent? So this means that in this top cell, you need to design this semi-transparent structure. You should make this electrode become semi-transparent. And this is usually done by using transparent oxide. So this is two configurations. So what's this advantage and disadvantage for these two configurations? So for this 2T tandem, because two cells are operated together, so it's a relatively easy process, but because they are connected, so you want this bottom cell and top cell to generate the same photocurrent, because they are connected in series. So this is called current matching condition. So for 2D tandem to be efficient, you want to meet this current matching condition. Top cell and bottom cell generate similar amount of photocurrent. This means they have more rigorous requirement on the band gap combinations. Faulty tandems doesn't have this current matching condition requirement, but of course it also has a requirement on band gap combination, but less strict than 2T. But because you need to design very large area transparent oxide, so this is a challenge because, as we know, this transparent oxide, especially ITO at the current stage, still have a relatively high cost, and also indium itself is a scarce metal. So this is probably one of the disadvantages of faulty tandem. So let's, so after introduce the basic structure for tandem, let's talk about how perovskite can work very well for these tandem solar cells. So perovskite have this ABX3 lattice structure. A cation, B cation, and X anion, their composition can be tuned. By tuning composition, you are changing the electronic structures, which means you are changing its band gap. So perovskite itself is band gap tunable. Band gap tunable is very essential for tandem solar cells, and it has other very good optoelectronic properties, meaning that it itself is a very good photovoltaic materials. So here is a figure shows how you change composition to tune the band gap of perovskite. So let's see here, when you, this is iodide and bromide mixed perovskite. When you increase the bromide ratio in your materials, your band gap is enlarged. And here, for around 40%, it has a band gap of 1.8 EV, which is suitable as a top cell of this tandem solar cells. And in this green circle, we see by changing lead and tin, so means changing the B side cation, you are also changing the band gap. By increasing the tin in the perovskite, you are reducing the band gap. And here is around 50% tin. You have a band gap of 1.25 EV, which is very suitable for the bottom cell. So by mixing iodide and bromide, you get a band gaps around 1.8 EV, which is ideal for a top cell. And by mixing lead and tin, you get a band gap of 1.25 EV, which is ideal for the bottom cell. And by combining these two subcells, you are constructing a tandem solar cell. So here come to our main topic is perovskite tandem solar cells, which as we know that perovskite itself is a very low cost semiconductor. And because it has such low cost and good optoelectronic properties, when we make perovskite as a tandem solar cell, it can greatly reduce cost and increase the power conversion efficiencies of a solar cell. So, as I already introduced, that in perovskite tandem, you have this top cell, which is bromide iodine mixture, and the bottom cell, which is tin and lead mixture. It has a band gap of 1.2 and 1.8, which is suitable for tandem. So this tandem concept is very we know that perovskite invented in 2009, and some efficiency progress come from 2012, and all of these are based on single junction. So in 2016, Professor Henry Snaith developed this tandem perovskite solar cells, and for the first time demonstrate it has its efficiency potential. So in this early work, so you can see that the mix tin with lead. By mixing tin with lead, they are continuous tuning the band gap of perovskite. At the 50%, as I already mentioned, they can get a band gap of 1.25, which is suitable for tandem. And another issue for this mixed tin and lead perovskite is that tin perovskite itself is easily oxided. In perovskite, tin element exists in the form of tin2+. But tin2+ is all not stable. When it is exposed to air, oxygen will easily oxide it to tin4+. And after oxidation, this perovskite layer will become have a lot of defect densities, which can significantly reduce the solar cell efficiency. And this is why it's very advantageous to mix tin with lead. By mixing tin with lead, you are getting a suitable band gap for tandem. At the same time, you are reducing the tin amount in your perovskite. So it actually a method can get suitable band gap and also reduce tin oxidation. So we can see that in this early work, they demonstrate first this bottom cell using this so-called inverted structure. So this structure might be a little different from what you already seen in previous lectures, which use titanium oxide as an electron transport layer. So in this structure, they use P.PSS on top of ITO glass, and P.PSS is a whole transport layer. So this layer can extract holes from a perovskite layer. And perovskite layer, of course, is a active layer generate electron hole pairs. And 660 is fullerene, is electron transport layer that can extract electrons from perovskite. So in this structure, hole is extracted to the ITO side and electron is extracted to the silver side. That's why it's called inverted structure, because it's a different direction compared with what we already seen in the normal structure perovskite. And by using this inverted structure, in this early work for the tin lead mixture, they got an efficiency of 14%. And as I mentioned that because they mix tin and lead, they reduce the usage of tin content in the perovskite layer. It actually increases the stability. So you can see this green curve, this yellow curve is a pure tin perovskite. It oxided very quickly in air, so its efficiency drops very fast. But by mixing 50% tin with lead, it actually stabilized the perovskite composition. When it operates in air, it greatly improves its stability. So that's why this bottom cell can work in the tandem configurations. So here, in this early work, both 2T terminal and 4T terminal are demonstrated. In this 2D terminal, this recombination layer is ITO layer. And 4T terminal, they make a semi-transparent top cell, which also use ITO as a transparent electrode. So for 2T, they got 17% PCE, and for 4T, it's 20% PCE. Which is a very good value in 2016. So here they show this SEM figure of this 2T terminal. You can see that this top cell composed of wide bandgap perovskite, bottom cell narrow bandgap perovskite, and in the middle you have this ITO recombination layer. And you have transport layer around on the side of perovskite to extract electron holes. So after 2016, this tandem concept become very popular and developed very fast. So this figure shows how it grows in efficiency over time. But until 2021, the efficiency of tandem is actually below single junction. Single junction perovskite at the current stage has the efficiency of 25.7, but before 2021, tandem solar cells, all perovskite tandem solar cells have the efficiency below 25. So as a concept, then it can have high power conversion efficiency. Tandem solar cell actually have lower efficiency than single junction perovskite. So it's not a very ideal development for this tandem. So here I will focus on introducing our recent work on high efficiency perovskite tandem. In this work, we demonstrate a 26.4% PCE, which is for the first time that a tandem perovskite, all perovskite tandem solar cell can have efficiency higher than single junction solar cell. So it's a very significant result for perovskite tandem, and sets the stage for continual advance of this technology. So before introducing the specific work, let's start from the basics. In 2D tandems, as I mentioned, you need the current matching condition. Top cell and bottom cell generate similar amount of photocurrent. How you can achieve this in all-perovskite tandem? It's not that easy because you can see this is the absorption coefficient of different perovskite materials. This is a tin perovskite, this is lead perovskite. Lead perovskite in general has higher absorption coefficient than tin perovskite. So this means when you want to generate equal photocurrent for two subcells, your tin perovskite layer should have higher thickness than lead perovskite. So here it shows a more clear calculation of what's the thickness requirement to reach this current matching condition. For top cell, when you have a thickness around 400 nanometers, 375 nanometer, you need 1.2 micrometer for narrow bandgap perovskite. So you can see there is a big difference in thickness to reach current matching condition. For narrow bandgap, you want a thicker layer. And for thicker layer, that means you want longer carrier diffusion length. This means you want your narrow bandgap has higher optoelectronic quality than the top cell. And it itself is a great challenge because narrow bandgap, as I mentioned, has tin. Tin itself can be easily oxidized. So in our previous work, we showed that when you design this 2D, 3D structure by using ammonium ligand to passivate perovskite surface, you can reduce this tin oxidation. This is the XPS structure. Then you can see in pristine perovskite, it already has a huge amount of tin plus 4. That means oxidation already happens. But when you add this protecting ligand, it reduces oxidation, it reduces tin plus 4 generation. But in our previous work, we use this 2D ligand called the PAI to passivate perovskite and find that it doesn't work well for thick perovskite films. When we increase the thickness to 1 micrometer, it generates an efficiency of 19%. It's a decent value for bottom cell, but compared with the required over 20% PCE, is still a low value. So in this work, we designed different 2D ammonium ligands with the hope that it can enhance the interaction with perovskite surface so it can reduce tin oxidation more efficiently. So PA is we already use, but not that efficient. So we added two other ammonium ligand. This one called CF3PA, we add fluorine atom here. By adding fluorine atom, because it's highly electron negativity, it can increase the electron positivity around this ammonium side. By increasing this electron positivity around ammonium side, we want to enhance their interaction with perovskite surfaces through this ionic interaction. So that's our basic design strategy, how we can use a newly designed ammonium ligand to try to enhance interaction with perovskite surfaces. This is a molecular dynamics simulations, so we can see there is a big difference. In conventional PEA cations, when we add on the surface, you can see the structure is not stable because it doesn't have strong interaction with perovskite surfaces. Many PEA cations just escape from perovskite surfaces, and you can see some iodide ions also escaped from perovskite surfaces. By enhancing the interaction using PA and CF3PA, because it has a higher electron positivity, it has a stronger interaction, it actually stays on the perovskite surface to form very compact passivation layer. And we think that by forming this compact passivation layer, oxygen can interact less with perovskite surfaces. So it's a very good strategy to reduce tin oxidation. So from DFT calculations, you can see this is different type of defects on the perovskite surface and how these ligands interact. By using the CFPA, it has much higher interaction energy with all the defects. That means it can interact very strongly with perovskite surfaces. And you can see that when you put ligands on top of surface, there are a lot of PA cations that are not absorbed on surface, it's escaped. But when you add this CF3PA on the surface, it all stays on surface to form a very good passivation layer. In the material characterization, we can see that all these ligands doesn't interact with bulk perovskite. It just stays on the surface and to form a surface passivation layer. So this is top seams. You can see that this CF3PA are mainly around the surface layer, surface region. But there's a huge difference in efficiency. For control perovskite, PC is here. For control perovskite, it's around 18%, which is what we usually got when we add this for this very thick bottom layer. And when we add different ligands, it all increase efficiency, but because the CF3PA has a stronger interaction, it increases efficiency more significantly to over 21%. So it's a very good strategy to improve efficiency, and this match with what we saw in the DFT calculation. So because of this good passivation effect, we can use thick layer in bottom cell to increase the photocurrent. So you can see different thickness have different photocurrent. When you increase the active layer thickness to 1.2 micrometer, we actually increase the photocurrent to over 32 milliamps square. And in the EQE spectra, you can see when you increase the active layer thickness, you have more sufficient light absorption on the near infrared range, which is for wavelengths around 800 to 1000 nanometer. So, as I mentioned, that tin perovskite has this significant oxidation issue. In control perovskite, in XPS, we see this tin +4 existence, meaning that perovskite surface are oxidized. But when we add this passivation layer, we see reduced tin +4, which means this strategy is very effective in reducing tin oxidation. So finally, because we have this capability to demonstrate such a good bottom layer with a thickness of 1.2 micrometer, so it can form a very good current matching condition with the top cell, we are able to demonstrate this 2T tandem with record efficiencies. So let me detail the structure of the 2D tandem here. We here use this 1.77 EV perovskite as a top cell, and nickel oxide as a whole transport layer, 660 as the electron transport layer. For the recombination layer, we use atomic layer deposit tin oxide as the recombination layer. The reason we use this tin oxide layer because this atomic layer deposit tin oxide is very conformal. So when you already make this top cell and when you want to process perovskite on top, because perovskite is solution processed, it's very sensitive to solvent. This conformal layer can protect the top cell from degradation because you are processing this this bottom cell. And for bottom cell, we use 1.22 EV perovskite, which is tin lead, P.PSS as a whole transport layer, C6 electron transport layer, and then another atomic layer deposit tin oxide as a protection layer, and then the copper electrode. So this is the SEM of specific device structure. You can see that this bottom cell is much thicker than the top cell because we want to reach this current matching condition. So because we use this good passivation layer in the bottom cell to improve the active layer thickness, we can actually get this tandem cell, get a very high efficient tandem cell with very high photocurrent. By increasing the bottom layer thickness from 700 nanometer to over 1.2 micrometer, we get a current density of over 16 milliamp square centimeter. So it's a very good value for this tandem configuration. And this in the EQE spectrum, we can see that because we are increasing the thickness, we get more sufficient light absorption in the near iron region, so we can get higher photocurrent. So this is a record efficiency for perovskite tandem cell, which is certified efficiency of 26.4%. As I already mentioned, this is the first time that perovskite tandem cell can have efficiency higher than single junction. So it's a very significant result. And you can see in EQE is a very good current matching. Bottom cell and top cell generate similar amount of photocurrent. And we also, so this is a very small area. For a large area, over 1 square centimeter active area, we can still maintain an efficiency over 25%. So it means that there's a possibility for this type solar cell to be scaled up. So after talking our recent breakthrough in efficiencies, I want to talk about what's the limitation in this current technology and how this technology will develop in the future. So to begin, we need to really analyze the cost of perovskite tandem solar cell, because once you have this cost and analysis, you know what specific parameters you want to achieve in your solar cell, you can then develop a technology to reach this target. So this is analysis reported by Peking University in China. They calculate that perovskite tandem, because it has higher power conversion efficiency than other technology, has the lowest cost projected. But this cost, to reach this low cost, you need two requirements. First, you want your module lifetime to over 15 years, 15 to 20 years. So that's a very huge challenge for perovskite, because we know that there's there are a lot of stability issues that impede perovskite technology to be stable over 10 years. And the second, you want your this technology to be efficient. Here they use a very conservative number, 22% PCE. But even for this 22% PCE, is hard to achieve, because here we are talking about solar modules. In real applications, we are using solar modules to generate electricity, and solar modules have very large active area. But in the previous demonstration, which has very high efficiency, we are using solar cells to achieve this this high efficiency. And solar cells have such a tiny area that it's not suitable for practical application. So it immediately comes to the current weakness of our technology. First, the stability is not that still cannot satisfy the 15 to 20 years requirement for a low cost scenario. Second, efficiency itself is demonstrated, but it demonstrates on a very small scale. So we need large area solar modules to achieve this efficiency requirement. So first, let's talk about stability. What's the stability issue come from? The first thing come to head is in top cell, we use iodide and bromide mixture, but iodide and bromide mixture perovskite is not stable itself. So you see here, this is a PL spectra of iodide bromide mixed perovskite. In the beginning, it has a band gap around 1.8 EV, but after light illumination for just 60 minutes, its band gap quickly shifted to 1.7 to 1.7 EV. That means after light illumination, there is a band gap reduction for this iodide bromide mixture perovskite, and this is called phase segregation, highlight segregation in perovskite, because iodide and bromide mixture tend to and become phase segregated. There will be iodide-rich region in perovskite, bromide-rich region in perovskite. And once this iodide-rich region generated in perovskite, the band gap of perovskite will greatly reduce, which is not suitable for tandem because tandem is very strict on the band gap requirement. Of course, you can have different strategy to reduce this iodide bromide segregation issue. And in this particular work I'm talking, they use formaldinium cesium mixed perovskite composition and find it can reduce this phase segregation compared with MA perovskite, but still you can see that there's still some tiny shift over time and in 1 hour, but we are talking of in practical application for 10-year, 15-year stability. So it's still need a great improvement on this strategy. So this is a specific figure we show in our work. We use 40% bromide mixture and the 1 sun illumination, its band gap remains stable, but under very intense light illumination around 5 sun, you can see this ion migration happens. Sorry, this phase segregation happens. So it reduces band gap, which is not ideal for tandem. So this is the stability curve we obtained for our tandem solar cell. After 600 hours, there are already a significant degradation, and this is mainly caused by this highlight segregation. In bottom cell, there are also stability issue. As I mentioned, bottom cell using P-dot PSS as the whole transport layer, but P-dot PSS itself is not a stable whole transport layer. It has limited thermal stability. So in this work done by Professor McGahey, they show that under 85-degree aging, your solar cell efficiency drops very quickly for bottom cell, and it mainly attributed to this P-dot PSS layer. So in this work, they show that very interesting that even without whole transport layer, thin layer perovskite can still work. Because they get rid of this whole transport layer, they actually get very good very good stability for this thin layer cell. They demonstrate various stability tests. For example, this damp heat test, anneal at 85 degree and 85 relative humidity, they can be stable for 1,000 hours, which is very astonishing value. And they did this operational stability also reached to 1,000 hour stability, but you can see already after a long time operation, there is some degradation happens. Even though they reduce this P-dot, replace this P-dot PSS, there's still some stability issue. And when they replace this P-dot PSS, this efficiency of bottom cell actually reduced. So as I mentioned in the record cell, people still use P-dot PSS to get record efficiencies. There's still a lot of work need to do to get high efficiency without P-dot PSS. So this is an outlook for the stability test, and for in perovskite community, people using different parameters to evaluate stability. For example, they include different temperature, different atmosphere, and using with light, without light illumination, and different operating conditions to evaluate the solar cell stability under different conditions. So for tandem solar cell, because there are different degradation mechanisms, you need to evaluate their stability under different stability tests. For example, tin itself in perovskite is very easily oxided. So you want to evaluate how atmosphere can influence the stability of tin perovskite. That means you need this ambient humidity test for this tin-based perovskite. Highlight segregation is something happening in top cell and accelerated and light illumination. So when you want to evaluate highlight segregation, you want your solar cell to operate it and light illumination to evaluate their performance. And finally, for the whole tandem cell, you want to evaluate its real operation stability and the real life conditions. So you want all these different aging parameters, for example, temperature, atmosphere, light illumination, combined together to evaluate this tandem cell. So in the future, to standardize this tandem solar cell stability test and to elucidate specific degradation mechanisms, people need to design different stability tests customized to evaluate stability of tandem cell. Finally, another issue is scalability, because as I mentioned, the record efficiency are demonstrated for small area solar cells, but in reality, you want perovskite solar modules to operate under real life conditions. So that means you need to replace spin coating with different scalable fabrication methods. There are different fabrication methods can be scalable, for example, blade coating, slow die coating, and spray coating. But at the current moment, to use this method to develop efficient perovskite solar cells is still an ongoing topic. And also when you design modules have this specific requirement for design. Modules are different subcells connected each other. So when you have designed this module structure, you need to specify how these different subcells are connected, because when you connect different subcells, you are creating some dead areas and cannot harvest photocurrent. So you want this dead area to be as small as possible for good module efficiency. So finally, I want to just share a recent work developed by Nanjing University in China, how they try to demonstrate scale-up potential for tandem solar cell. In this work, they use this blade coating to make both top cell and bottom cell to be scalable. So this is device structure and how they use different methods. You can see that they use blade coating for perovskite fabrication, evaporation for transport layer, ALD for this recombination layer. All these processes are scalable. So because this scalable process, they can get 1 centimeter device over 25% around 25% PCE. And they also specify their module fabrication. They use this so-called double ALD layer to protect perovskite during this module fabrication and get a good module efficiency. And finally, they demonstrate modules with 20 square centimeter active this area and get efficiency over 22% for tandem solar cell. So you can see that there's possibility for tandem solar cell to be scaled up by using all this scalable fabrication. And in this work, they already demonstrate this potential, but the efficiency is 22%. We mentioned earlier that in small area, we can get over 26%. There's 4% difference coming from the scaling up. And that's something need to be addressed in the future. So finally, I want to show this figure then to conclude my today's presentation. We are all talking about very high efficiency perovskite solar cells, but they are all small area solar cells. In reality, for practical applications, people need to develop solar modules. And this is this from Unreal chart, what's the current efficiency for solar modules. You can see silicon all have over 20% PCE with very large area, and that's very similar to what they got for small area solar cells. So silicon module and solar cell have similar performance, but for perovskite, this efficiency dropped to below 18%. So that means even though you can claim various high efficiency for perovskite solar cells at small areas, but eventually when you come to solar modules, there are huge efficiency drop, and that's something need to be addressed in the future for really commercialization of this technology. So as a final conclusion, we today talk about what's the motivation to develop tandem solar cells, how we demonstrate perovskite tandem solar cells, how we get high efficiency for tandem solar cells, and what's the critical challenges, including stability and scaling up for tandem solar cells. So that's my today's presentation, and look forward to your questions.
Thank you very much, Mingyang, for the very nice, detailed, and inspiring presentation about how to achieve this record efficiencies on tandem solar cell. So I will now go to the chat, and I will also ask at the same time people to raise their virtual hands for asking their questions. So the first one is coming from Govindaraj. What is the thickness of ALD tin oxide deposited between C60 and copper electrodes?
Yeah. Okay, let me quickly come to the related.
Yes.
So this tin oxide layer have thickness around 15 nanometer. It doesn't show here. So why we use 15 nanometer? So first, because we want a very conformal layer to completely cover the top cell. So when you when you fabricate this bottom cell, you don't the solvent will not leak through this tin oxide layer to destroy the bottom cell. Sorry, the top cell. And second, tin oxide layer itself has limited conductivity. When you get very thick layer, for example, over 20 nanometer, 30 nanometer, you are introducing a lot of resistive loss. So we find 15 nanometer is the most optimized thickness because first, it protects the underlying layer. Second, it doesn't introduce extra resistive loss, so it can get a very high efficiency.
Thank you very much for the question, and Mingyang for the answer. From the same person, we have another comment and question. Exciting talk. What is the efficiency of your latest monolithic 4-terminal based perovskite tandem?
That's a very good question. So for 4-terminal, we are actually not demonstrating much on 4-terminal. We are mostly focusing on this 2-terminal configuration because first of all, 2-terminal is more challenging in engineering because you want to fabricate 2 subcells together, and itself is technically very challenging. The second, for this 4-terminal cell, you want very good transparent oxide layer, and that's not our specialties. Our specialties is mostly on perovskite fabrication. So we didn't demonstrate much 4-terminal tandem. Our most work is focused on 2-terminal, but it's a very good direction. And I think the current record for 4-terminal also around 28%.
You mean, sorry to comment here, but you mean 28 on perovskite?
4-terminal, yeah. I think that's recent it's not our work, but that's from literature, yeah.
Okay, interesting. So there is another question from Timur Maksudov. Have you used any other material instead of gold for the recombination layer?
Yeah, that's here I see. Recombination layer, we use a 1 nanometer gold because first of all, it's very when we use ITO layer, that's another choice. When you use ITO layer, you have a thickness of 100 nanometer, and this 100 thickness nanometer will introduce a lot of optical loss. So we find this 1 nanometer gold, it can facilitate recombination and electron hole very efficiently, and because it's only 1 nanometer, so it doesn't influence optical transmittance that much. So we find it's the most optimized recombination layer selection compared with this ITO layer. So that's why we stick to this 1 nanometer gold.
Okay, thank you, Timur, for the question, and Mingyang for the answer. Is there any other question or comment? I have some,
Yeah.
Mingyang. So my first one is, you demonstrated the halide segregation experiment,
Yeah,
right?
yes.
And you have shown at the maximum you exposed the films for 10 minutes.
Yeah, yeah.
Is the 10-minute time enough to test halide segregation?
So it depends on light intensity. So under 1 sun, under 10 minutes, it doesn't change. And for a very long time, like let's say tens of hours, it actually doesn't change. But when we increase the light intensity to 5 sun, this happens very quickly within 10 minutes. So you know that Hawke effect is Hawke effect is related to light illumination. So under light illumination, this highlight segregation is very quickly accelerated. So this is really related with your illumination intensity, and the very extreme light illumination, it indeed happens within 10 minutes.
So in order to achieve like
Yeah.
same result with 1 hour, how many hours you need to expose your film with 1 sun?
1 sun, for 1 sun, I think even when you're exposed to 24 hours, 48 hours, you doesn't see that much peak shift. So it's not a linear relation. It's not like 1 sun, 5 sun take 10 minutes, so 1 sun take 15 minutes. It's not linear. It's under very high intensity, it's accelerated much quickly.
Okay, I understand. But when you expose your solar panel at the end of the day, when you have a solar panel, it will be exposed to 1 sun, maybe 1.5 sun. So then why we care about 5 sun segregation if in 1 sun it will not happen?
So 1 sun it still happens, but it happens much slowly. 5 sun is more like an accelerated test. So we can see this phase segregation very in a shorter period of time. So I think this is one direction of perovskite stability test. Eventually, we are asking for 10 years, 15 years stability, but nobody can test your solar cell for 10 years or 15 years. So you need to design some accelerated test. And the short time, you get your stability results. And using this short time, you can predict the long term, how it can be stable for 10 to 15 years. So that's a important direction for perovskite stability. And I think at current moment, not many people are doing it.
Okay, thank you. And the last one, what is the light source you are using for this test?
This is UV illumination at around, I think, 450 nanometer. So,
and do you think it will play any role if you change the wavelength?
Indeed, perovskite are very sensitive to the wavelength of your light. UV light tend to degrade perovskite more rapidly than low energy light. So I think UV light is more harmful than other light, as this is also the case in normal single junction solar cells. Yeah.
Okay, thank you very much. I can see some more questions in the chat from Nisheka. Both 2T and 4T configurations are performing very well. So in your opinion, which configuration has more potential towards commercialization?
Oh, well, this is a very good question, but to be honest, I don't know. I am not an entrepreneur to predict what the future of perovskite photovoltaics. But as I see that the 2T terminal is more difficult to fabricate and very rigid on band gap combinations, very rigid, very strict on current matching conditions. 4T doesn't have such rigid requirements, so it's easier to fabricate and has a relaxed requirement on band gap combinations, but 4T also require large areas, this transparent oxide layer, which at current moment can be a huge disadvantage in terms of cost. So both of them have their own advantage and disadvantages. So in the future, who wins this final race, I don't know. Yeah.
Thank you for the answer. Another one is from Mohamed Faraj. A question: as we know, the 2T perovskite silicon based on high and low band gaps, but the whole device, what is the band gap?
So if I'm not wrong, you are talking about the band gap for perovskite and silicon itself. So in 2T perovskite silicon tandem, silicon itself has 1.1 EV band gap. Perovskite has a band gap of 1.7 EV or 1.73 EV. When they combine together, in 2T tandem, because you have two semiconductors, you are talking about two different semiconductors with two different band gaps. You are not talking about the whole device with one band gap. So if I'm not wrong, I think we are talking about two subcells with two different band gaps. We are not talking about one single cell with one band gap. So I hope this answer is your question. Yeah.
Thank you for the answer. We have another one from Mustafa. Thanks. So the segregation rate increases with the intensity. Whatever was the way. This is already answered. So
yeah, UV is more harmful. Yeah.
Yes. Another from Timur Maksudov. Does the atmospheric condition play any role in halide segregation experiment? For example, should you do the PL experiment in glove box?
This experiment is done in glove box under nitrogen. But I think atmosphere indeed plays a role when it exposed to this high humidity condition. Perovskite tend to degrade faster, and specifically for how this environment influence halide segregation, this part I'm not very clear. I cannot give you a very clear answer, but I think moisture do play a role in the degradation of perovskite.
Thank you very much for the answer. I cannot see any other question. I cannot see any virtual hand raised. So let's thank Mingyang again. Thank you so much for this nice talk and for addressing all the questions and comments from the audience. It was a great pleasure, and thank you so much. So I can see now there is one. No, is there a virtual hand raised? No, I think it was by mistake, maybe. So thank you very much. And we can close this session now, and we can go for a lunch break, and we can come back in 1 hour. Thank you very much. See you later. Start the recording. So it's a great pleasure and honor for us to have in our first session after the lunch break with us Mr. Kai Olivier Brinkmann from the University of Wuppertal in Germany, the Faculty of Electrical Engineering and Information. So Kai is a PhD student there, and he's one of the experts of the topic of organic perovskite tandem cells. He has experience on the combination layers on metal oxides and the stability on both organic and perovskite solar cells. And as I already mentioned, the topic he will present us today is one of the most promising research topics and one of the the hottest research directions in the field of solution process photovoltaics today, entitled Perovskite-Organic Tandem Solar Cells. So it is a great pleasure to have you here, Kai. So I will now mute myself. So please share your screen and start your presentation. You have 45 minutes for your presentation and another 15 minutes for the Q&A session.
Okay, thank you, George. So maybe before you mute yourself, just make sure that my screen is visible.
Yes.
So
it
can
is.
everyone see my screen? Okay, very nice. So my I will be here to talk about perovskite organics, but I will also go a little bit on to the general of why we do perovskite multi-junctions. So I guess you already heard a little bit about this before, but yeah, well, if it's a repetition, you can just hear somewhere else and continue with the moment when we get towards the organics. But yeah, well, the first slide I think I will make very quick, because this is something that you already know, that the perovskite is a crystal and it has this ABX3 structure. And yeah, probably you also know, I've already seen this graph, that the main, or one of the main things why we want to use the perovskites is the defect tolerance, so that we mainly generate shallow trap states instead of deep trap states, which enables us to make, let's say, rather dirty perovskites and still get pretty nice performances out of them. And yeah, well, this is just an illustration showing how these trap states would be positioned inside the band gap. And this enables us to, well, as George already said, to solution process of perovskites. And this is something that is, and not only for the single junctions, but also for the tandem, is extremely important, because it enables us to use a large variety of different deposition methods. For example, we could just mix the precursors, make some kind of deposition technique to make a thin layer, anneal them, and we get a perovskite. And these kinds of perovskites, if we do it the right way, they actually already give us a decent active material for solar cells. And how to get this thin film? There are large amounts of techniques that we could use. So in the lab, we usually use spin coating, which is not really upscalable, but a nice tool to make it, to do it on a research scale. If we want to upscale, I think Michael will be talking a little bit about this after me. There are different ways. So for example, to get the same results as spin coating, we could blade coat, slot die coat, spray coat, inkjet print, and all of these different technologies of how to make a thin film of a precursor. And to get you a rough idea how, let's say, easy it is to make such a perovskite layer, I just brought a video where we use the spin coating technique. Actually, we use an additional step, which is called the gas quenching. So this will not be my main topic, so I will just be very brief about this, but it's going over the intermediate state. We put it on a hot plate, and now we already have the active material that is this is able to be a solar cell in the end, which is of course much easier than if we go for the classic technologies like silicon, gallium arsenide, and all the classic semiconductors that we use for solar cell technologies. Another downside, or let's say downside, of the silicon technology is that it's basically plateauing at the moment. So we're not getting really much better anymore, and we are already approaching the theoretical limit. And if we're talking about perovskite single junctions, we're actually also going in this direction. So when you go back, you see that the progress is much shorter, so we are much faster in the development, but we are also hitting this leveling up here where the efficiencies just don't want to rise anymore. And the way to go around this is perovskite silicon tandem, and eventually, hopefully, perovskite-organic tandem, which I hope I can convince you that it will be a good idea to do. Well, another thing that you probably already know about is the direct band gap, which enables us to make the perovskite layers very thin, which is also important for the tandems, because we just imagine that we would now have a high efficiency. So all of these applications that I'm just showing here, they typically have very poor efficiencies. And since we can make the perovskite very thin, we are able to make flexible and also semi-transparent devices, which makes applications like this possible and also reduces the cost. So we know we can solution process. We have a very, very low amount of material that we have to use, which in the end reduces the energy demand, reduces the cost of such a device, and of course, in the end, the energy payback time so basically the time that we need until the energy is there. And this enables us to make all of these cool applications that we see in, or that you may already have seen in some publications and also in some newspaper articles. Those are currently pretty low performing organic solar cells, but all of these applications are viable even with the perovskite tandem technologies that I will introduce you to now. The reason why the tandem technologies work in the first place is the flexibility in choice of composition that we have in the perovskite. So we can basically tune the band gap by mainly tuning this X part on the perovskite composition, which enables us to go from band gaps like 1.2 to band gaps of exceeding 3 electron volts, which gives us a huge play park to play around and build different kinds of solar cells. And of course, we want to build tandems in the end out of them. Having a look at what we would expect. So we are in the climate crisis. So the main reason why we want to build solar cells in the first place is you want to replace gas. We want to have the carbon footprint as low as possible, which means in our case, we have to get rid of the energy consumption. So we need to make sure that we need as little energy as possible to build our solar cells. And here we have two different advantages of the tandem concept, which is basically, if you just have a silicon solar cell, we see the carbon footprint is pretty large. If we would just put a perovskite solar cell on top of a silicon substrate, silicon solar cell, we would increase the efficiency. So this is the current world record by a lot, while increasing the carbon footprint just by a very small amount. If we then would actually get rid of the silicon, we could even go down here, and so basically reduce the carbon footprint by a factor of 4, while the efficiency should be quite comparable, which is pretty promising in my opinion. Just a little bit of before I go into all into tandems, a little bit of an overview what else we are doing in our labs. So we are not so typically when you want to put something to market, you always care about how to get the cost down, how to get the stability up, how to get the efficiency up. And we do a lot of work on the cost side, where we work on the reproducibility, the scalability of the techniques that we're using. So for example, we use a lot of ALD, which is, if you're interested in this, please have a look at this publication here. So you can see that ALD is not necessarily a thing that takes a lot of time and a lot of money. We were working on replacing expensive materials like the ITO, for example, which is, I think, one of the main cost factors. So I think, again, Michael will tell you a little bit more about the cost aspect of also ITO, which is striking in with the perovskite. We did a lot of investigation about stability. So we were using internal barriers to bring up air, illumination, and temperature stability of a perovskites. And of course, that's the main topic of today. We are working on tandem solar cells. First of all, why would you need a tandem solar cell? The main reason for this is the so-called Schottky-Queisser limit, which says that we have a hard cap to the efficiency of a single junction solar cell. So if we have a good single junction solar cell, we would have a fixed band gap. And this band gap defines what kind of photons I can absorb. So for example, if I have a band gap of like this red line here, I would be able to absorb all the photons above the band gap, but I would transmit all the photons below the band gap. So all of these photons would already have been lost to energy transferation. While all the high energy photons, so this is the other limit, are limited to the energy of the band gap. So every photon which has a higher energy than the band gap excites an electron far beyond the conduction band, from where it relaxes down to the conduction band. And all the difference here, all the energy is going into phonons, which means it will basically heat up the device. So it's called a so-called thermalization loss, but it will not contribute to the electric energy that we get out of the device. So we have to get around this. And the straightforward way to do this is to split up the energy conversion. So we will not use only one solar cell, which absorbs the full spectrum, but we use a high gap solar cell, so a solar cell with a very high band gap, which is able to very efficiently absorb the high energy photons, generate a large portion of energy per photon. And then a lot of the charge carriers that are transmitted are then absorbed by a low band gap perovskite, or basically low band gap solar cell. If we now combine both of these efficiencies, we would have a higher efficiency in power conversion than if we only have one of those, because we are significantly reducing the thermalization losses. And to give you a rough idea where this can lead, this is the so-called annual efficiency chart. I don't know how often you have seen this already. Just in case you did not, it basically gives an overview of all the solar cell technologies in research. So this is research efficiency records that we get. And if you look a little bit up here, so all the purple ones, all of them are multi-junction solar cells. All of them are tandems, triple junctions, quadruple junctions, and also this very high record efficiency here is actually a tandem solar cell. The downside of these kind of solar cells is that they're typically very expensive. So they're usually not used at all inside on the Earth's surface. So they're on the Mars rover. I think one of those solar cells is currently in use, and of course the ISS and all the space stations, they need very high efficiencies, and you don't care about cost. So this is something where you can use this, but for Earth application, we typically using at the moment single crystal silicon gallium arsenide. And the two technologies that I want to introduce, or basically the one that you already know and the one I want to push you a little bit about, is the perovskite and the organic, where we already see that the perovskite is already very close to where the silicon is at the moment, and the organic is a little bit lower, but we will see that this is actually not necessarily a problem. We can also see that the perovskite silicon tandems are already exceeding the efficiency of the pure silicon. So we already have a tandem concept that is superior to a mere silicon substrate. And with this kind of setup, I will start up and having a rough idea what kind of tandem devices I'm able to build. Because the easiest way maybe to build such a solar cell, such a tandem solar cell, is just building a semi-transparent perovskite solar cell, so a semi-transparent wide bandgap solar cell with two electrodes, like I'm just using. So this is basically the equivalent circuit here, and I'm just mechanically stacking it on top of a silicon solar cell. This means that I don't have any requirements how to connect both of them, right? So I take this kind of, I take these two, I choose these two pins, put them to my power supply. I'm making an AC voltage out of them, and I'm fine. So I can basically do whatever I want with these kind of solar cells. But I have to have this transparent electrode, and I have to manage the optics somehow so that the light is coming out of the wide bandgap solar cell into the low bandgap solar cell, which can be a little bit tricky actually. A way to circumvent this is to use a so-called two-terminal or monolithic tandem solar cell, where the silicon solar cell and the perovskite solar cell are directly connected. So we are directly processing the perovskite solar cell on top of the silicon solar cell, and we usually need an interconnect in the middle, and we will come to this in a minute. But something that is important for us, if we talk about these kinds of solar cells, we have a series connection and we cannot do anything about it. So we have two terminals, so two pins where we get a voltage or current flow or power out there, which means that the silicon solar cell and the perovskite solar cell, or in general the low bandgap solar cell and the high bandgap solar cell, are serial connected, which means that we need So that this is like Kirchhoff's law. All the current going through here needs to be the same current as it goes through here. And a perovskite is, in a first approximation, a current source, which means that if this current here is lower than the current produced by the low bandgap solar cell, the lower current would limit the current of the higher performing solar cell. So what we always have to have is a kind of a current matching, which is done in an electrically and an optic way. So we have to make sure that our devices really hit the point where we want them to be. So we basically have, two sets of, we have downsides on both sides. So we have the two transparent electrodes with the 4-terminal device where we have to make the optics work. And we have the 2-terminal device where we need the current matching, and we certainly need an interconnect to make both of those solar cells work together. But lucky us, both of them are currently very successful. So for the 4-terminal and for the 2-terminal solar cells, there's currently records of beyond 30%, which is pretty promising, I think. Something that is also pretty interesting is that especially for the 4-terminal tandem solar cell, which I personally believe might be the first thing that might come to market, we have the opportunity to integrate the solar cell into the glass encapsulation of the silicon modules. So we could basically process our perovskite or semi-transparent high-gap perovskite solar cell on top of the glass encapsulation, and thereby build a tandem solar cell without really having to change the production line. So I could imagine that this might be the first thing that we will see on the market. But the huge downside that we still have is we still have a silicon solar cell. And we just learned in the beginning, of course, we will increase the efficiency without having to add too much of additional power in uptake, but we will still have the downsides of the silicon, like high temperatures, high energy consumption, high purity requirements, and in the end, the high carbon footprint, and therefore the long time before we can go for real positive a positive yield of power out of them. So we want to get rid of the silicon, and you already heard about it. So I think we are not as good, but we are also working on it. So we could use the low bandgap perovskites as a partner for the perovskite. A low high bandgap perovskite, we will not have the problem of having silicon over there. And here we're working with these wonderful people together with the University of Potsdam and of Oxford. And we actually got roughly 26%. This is not the best on the market. Once again, the current world record is at 28, and I'm pretty sure you just saw it some hours ago, so I'm not going into detail. But something that I will be going into detail is that all of those perovskite tandems need tin. And tin is a little bit of bad news, let's say it like this, because currently no one found a solution to fixing the fundamental stability issue of tin. Because if you add tin into the perovskite mix, which is something that you have to do if you want to go for low bandgaps, then this tin is typically oxidized 2+. And the thermodynamic best state is a tin actually oxidized 4+, which means that we have an intrinsically thermodynamically unstable material which really wants to form this tin 4+, where, well, it depends a little bit on who you're believing. If they're doing a bulk doping of the material and therefore increase parasitic recombination and reduce perovskite performance, or if it goes at the interface and reduce and increase traps and increase parasitic recombination, but in the end, all of them are deteriorating your solar cell. And honestly, I really hope I'm wrong about this. because I really like these efficiencies. I'm not sure if we will ever be able to. So the potential of a perovskite tandem is a little bit higher than of the perovskite-organic tandem that I will be talking about later. But I think as a community, we should be prepared that it's possible that this might never be stable in the first place, that the efficiencies are very good. And I know people thought the same thing about the pure perovskites, and we are now talking about market introduction, but we should still think, or keep in mind that it is possible that those materials will not suffice. And then we need an alternative, basically a fallback scenario, where we could go, which we could use if we simply don't have the option of using a low bandgap perovskite stability-wise. And for this, we are not using, so I already spoiled it a little bit, we are not using the perovskite, but we are using an organic solar cell, which is down here. And here in this annual efficiency chart, so we can see that something happened over the last years. So here for the organic solar cells are these full red dots. And we see that for quite some time, the organic efficiency basically leveled. And then here in 2019, there was basically a technology, let's say, it's not a jump, it's not a step, it was basically an explosion when efficiencies went up big time because of the introduction of the so-called non-fullerene acceptors. And what these acceptors do, so they are non-fullerene, so one could figure that before 2018, most of the organic solar cells were made with fullerene as an acceptor. Now we're using non-fullerenes as acceptor for the organic solar cells. And those non-fullerenes have two nice advantages. The first is that charge separation is pretty nice, which is a tricky thing in the organics. But the next interesting thing is that we have these absorption extending far into the near infrared. Same here, if you look at external quantum efficiency, we see that the absorption actually, or the external quantum efficiency actually goes far into the near infrared, which makes it very, very interesting for tandem applications. This is something, of course, that we tested, and we just have put all of this into our computer, into our optical simulation. We use transfer metric simulation from SetForce and just put very conservative assumptions in there. So we assume that we have a fill factor of 80%, a voltage drop of 0.5 in each solar cell. And we saw that already with these very, very conservative estimations, we should be able to already go for 24, 25, almost 26%. And if we do the whole thing a little bit more optimistic, so still realistic, so it's not like this is undoable, but if we go for a fill factor of 85% and a voltage drop of 0.4, just as an assumption, we should be able to go beyond the threshold of 30% pretty nicely. So I think, or we think, that this technology is highly promising. But wherever there is promise, there is also a challenge. And in our case, the challenge was that if you look into literature, it doesn't really look like the advantages of the organic solar cells in terms of stability are actually there. So all the non-fullerene acceptors, based solar cells, if they are in light, if you put them on the solar simulator, they degrade swiftly, and not just a little bit, but drastically. But so this is now the upside. The upside is that we found that this is not necessarily the case if we are thinking about perovskite-organic tandems. So what did we do? We built ourselves an organic solar cell. So we started out with a so-called binary junction, which is like super unstable. Then we use, so here you see the time, and here you see the efficiency. So you see the development of the efficiency over time. And you see that, well, the binary junction, so this is just a way of stabilizing the composition. An unstable composition is really degrading like crazy. If we mix in a little bit of fullerenes, it stabilizes the matrix and makes the solar cells a little bit more stable. But you see again here we are talking about 100 hours and 90%. So we have lost already 10% of efficiency after 100 hours, which is not acceptable. But here on the left side, we see the illumination spectrum that we used for these kinds of degradation experiments. And if we plot the absorption spectrum of our organics in here, we see that, and especially also the absorption spectrum, the band gap of the perovskite, we see that this part of the spectrum actually would never reach our organic solar cell. So we would only have the near infrared part of the illumination spectrum. And if we now operate the solar cell, so we will use the same amount of photons, so the same amount of charge carriers generated, just with a different band energy gap absorption, so just with a different light color actually. And we see that the stability actually goes up drastically. So I actually had to put a break into the x-axis. So here you see I'm jumping from 100 to 1,000, 3,000, 5,000, because in this time scale you're basically not able to see any decay. And in the end, we had roughly 5% of decay after 5,000 hours of continuous illumination, which is something that it's simply impossible with a lead tin based low band gap solar cell at the moment. And once again, this illumination scenario is actually what is happening inside a tandem. So we are pretty sure that we have here an alternative which is stable enough to replace the lead tin perovskite. Anyway, when we started out the project, if you looked into literature, these kinds of Perovskite-Organic tandem solar cells, they were pretty bad. So we ended up with, the highest efficiency in end of 2021 was roughly 20%. And the main reason for this was that this interconnect was really, really lousy. So why I want to talk about this is because we have to connect an N contact from the perovskite solar cell. In our case, this will be tin oxide, and the P contact of the organic solar cell, which will be moly oxide in our case, and somehow get the charges from an N to a P contact without forming a junction. So why this is a problem, it's pretty easy to see, because if we don't use an interconnect, we would form a PN junction or a depletion zone in the middle with a dBi length, so with a dimension which is too wide to tunnel through. So the charges coming from the N contact towards the P contact would be blocked. And as a result, we would end up with such an S-shaped JV characteristic, which is highly unfavorable for a solar cell in general, not only a perovskite solar cell. And what we can do, oh, I'm sorry, this is still in German. I will translate it. We can insert, so here in this point, we can insert an interconnect. And this interconnect will have a very high charge carrier density. And since the dBi length is proportional to 1 over the square root of the charge carrier density, we will see this distance shrink, which means that the barrier might still be there, but it's so narrow that the electron is able to tunnel through into the wideband, into the high work function material. And we would end up with a JV characteristic that is actually well behaved. So here we were talking about fill factors of, I think we had roughly 50, 40, 50 something percent of fill factor, and here we're talking about fill factors of 75 to 80%. And now we are coming to the reason why the solar cells from 2020 or the end of 2021 were less optimal was that this interconnect was realized by introducing 1 nanometer of silver. So we just evaporated 1 nanometers of metal in between those two contacts. Of course, the metal has a high charge carrier density, so it's very nice there. It's able to facilitate the interconnect. But this is now from our own paper here, if you use the 1 nanometer of silver in between the interconnect, you already have a severely reduced transmittance. So this one here is the optical transmittance. Of course, we have different optical effects, so this will not be 100% the same as if it's integrated in the device, but we can see that it's far from being 1, which would mean that it's an ideal interconnect. And to get away from the silver, we introduced an 1.5 nanometer thick indium oxide layer. So yes, of course, it's again indium, and I talked about that indium was expensive, but still it's very, very low amount of indium oxide. So I hope it will still suffice. It will be not close to the amount of indium that we need for an electrode. And already these 1.5 nanometer of indium oxide were able to bring us the same effect. So the S shape was gone. And if you look at into the optics, so if you just compare the 1.5 nanometers of indium oxide and silver, we see that the transmission goes up big time. So this is now the tin oxide, the indium oxide, and the molybdenum oxide. So we have basically the N contact, the interconnect, and the P contact together, and all of them together have on most of the parts. So we are mainly talking about near infrared, of course, because we want to transmit into the organic solar cell, and the transmittance is far beyond 90%, which is significantly better than what we get for silver. And if we do the comparison in the EQE, so this is just the current of the organic subcell, so external quantum efficiency of the organic subcell, and we see that by just replacing the silver with the indium oxide, we gain a total of 1.5 milliamps per square centimeter. And considering that we have an open circuit voltage of 2.1 volts, this 1.5 milliamps per square centimeter gave us over 2% of overall efficiency. So here, is not the best device, so it was just a device that we used for comparison, but already here, just the same device, just used different kinds of interconnects. We went up from the 20.5, which is roughly the same that we got in literature, to 22.8% without having to do anything else. Additionally, some optimization also on the perovskite subcell that I will be not going too much into detail here, actually then propelled it up to 24% here. Here you also see the current. So this is basically the same current that we got here. So here we got the current. We optimized a little bit on the fill factor. We optimized on the VOC and ended up with an efficiency of 24%. So this is currently the world record for this kind of device. And we're even able to certify those values. So a little bit lower because the certification process is stressing the devices in a way that it's not done outside. We got a confirmed value also from the Fraunhofer Institute, which is very close to the 24% that we got here. And yeah, well, anyway, we think that this is just a start. So we think that we should, especially as the perovskite community, that we will invest much more effort in this kind of tandem technology, and that we should be able to reach these 30% in the nearer future, and yeah, well, hit maybe the 31, not only for the perovskite, but also for the perovskite-organic in the future, while not having the downside of being fundamentally unstable. One of the things that we will have to do for this is this is a little bit like a homework for the chemists, because this is something that we as engineers are not able to do anything about. One of the things that we have to do is we have to bring down the energy gap of the organic absorber. So we have to move from the 1.33 where we are at the moment, which would limit the efficiency to 29, which is still impressive, but not perfect, down to almost 30, these sweet 30, 31%, which would, yeah, will certainly overcome the best silicon solar cell that there will ever be. And in the end, so let's just have a look at the, at this annual efficiency chart again, where we think that we could be with this kind of technology would be actually up here. So even outperforming the currently best perovskite silicon solar cell. So in general, we think that this kind of technology, it will see some serious attention in the next years. So for everyone who was asleep due to my boring voice and is waking up, this is now a little bit of the take-home messages. For the perovskite, as probably since you're here, all of you know, it's highly promising technology. We are have very high efficiency. We should be able to be easier in processing and much cheaper. The thermal budget is just crazy low. And we have this bandgap tunability, which enables us to build multi-junctions out of these devices. We can do 4-terminal and 2-terminal devices, where we either have transparent electrodes to care about, or we have the interconnect, which we talked a lot about. And in the end, from the cutting edge, I discussed a little bit the Perovskite-Organics and also the interconnect and how this 24% were possible and where we should be able to land in the future. With this, I would like to thank you for your attention and also this little spot advertisement for our own sakes, because we're currently hiring. So if you're interested in a PhD position and you want to work on Perovskite-Organic tandems, please give either my boss or me an email and we look into this. And so I'm looking forward to your questions.
Thank you very much, Kai, Olivier, for the very interesting and inspiring presentation about this very interesting and hot topic on solution process photovoltaics. So it's now time for questions and answers. So I will first check the chat. We have one question from Timur Maksudov. Thank you for the interesting presentation. I have 3 questions. So number 1, let's go one by one. Number 1, have you investigated what is the optimum thickness for both perovskite and organic layer?
Yes, of course, you actually have to do it. So let me see if I can. So for these kind of simulations that I'm showing here, for these kind of simulations, you always have to consider all the layer thicknesses. So this is part of the optical optimization. And so I don't know them by heart. I think we are currently at 400 nanometers for the perovskite solar cells, and we have roughly 110 nanometers for the organic. But actually, there is not one optimal thickness, but there's one optimal thickness for every single point on this graph. So it always looks very easy to show this graph, but in the end, it means that for every single point here, you're tuning through all the possible thickness combinations of the perovskite and the organic solar cell, and then get the one thickness combination that gives you the highest efficiency. So in the moment when we would walk over from here to maybe here, we would of course have to adapt the thicknesses of the absorber layer.
Thank you very much for the answer. Let's go to the second one. Based on band gap of perovskite, it seems that in tandem configuration, only Y6 absorbs in the NIR photons. Is that sufficient for the organic layer to operate as a top cell?
Oh, I love this question, because it actually gives me opportunity to talk a little bit about the organics and the stability actually. So the short answer is yes, it's certainly enough, because exciton generation in the non-Fourier acceptor is totally sufficient to generate or to get a good solar cell. which is also like if you, so the JV characteristics, if we tune up the infrared source, is good to get the high current out of them. And we actually think that the reason why our organic solar cells are stable is the fact that only the Y6 is absorbing the light. So we, for example, we did some kind of an experiment where we illuminated the PM6, which is the polymer, and the Y6 with white light, and we found that the PM6 is actually much less stable than the Y6. So it's not only sufficient, but it's actually a good thing that only the Y6 is excited, because the Y6 seems to be much more illumination stable than the PM6. And yes, we are. Maybe I'm answering the third question directly in row. Okay. So you also asked about the halide segregation. Yes, I skipped this because yeah, for time's sake, because this is actually another part of the paper. So please have a look in here if you're interested on how the halide segregation actually works. At the moment, it's a problem. Yes. So we basically did the we exchanged the whole transporter, and we were able to reduce halide segregation by roughly an order of magnitude. So we went from a stability of 5 hours to 100 hours, but we're still not optimal. So I have to be totally honest there. Halide segregation is currently, I think, one of the main limiting stability concerns for these kinds of perovskite-organic tandem solar cells, because we have to go up for this 1.85 EV, which is pretty high in terms of band gap, which is another reason why we want these lower band gaps, because the lower we can go in the low band gaps device, the lower we can also go inside the wide band gap device, and this will also increase the stability. Even though I think for these high band gaps, we actually have the most stable solar cell at the moment, but still 100 hours is not enough. So yes, it is a problem.
Thank you very much for the detailed answer. Let's move to the next one, which is from Yidia. And the question is the following: is it possible to coat the interconnection layer by spin coating?
Not in the thickness, I'm afraid. I think that maybe, so I think it should be possible to do something like ITO nanoparticles or something in the interconnect. I'm not sure if there's an Sologil process giving you indium oxide and such high charge carrier densities. But I would say in general, it should be possible to bring some kind of an interconnection in there that is done by spin coating. It's hard, and it will certainly not be as thin and as optically transparent as the one that we built by ALD, because there's no way you can do 1.5 nanometers with spin coating. There's actually even no way you can reach the same values by just sputtering. So, or the reason why our perovskite is worse than high-run tons is mainly because our subcells are not as good as his.
Thank you very much for the answer. Let's move to the next one, which is from Apostolos Panagotopoulos. Thank you very much for the interesting presentation. I have one question related to the Tandem technology, which Tandem Perovskite OPV. Silicon seems to be more superior and sustainable for the future.
I would actually say yes and no. So if you're asking me, so we don't need more photovoltaics, we basically need a shitload of more photovoltaics. So I think at the moment it's smart to go for everything at the same time. So the same like perovskite solar cells, perovskite tandems are giving the better efficiency. Certainly, I don't argue with this, and they might be the solution if someone solves the stability issue. The perovskite-organic solar cells, they are more stable, but we have to solve the efficiency limit. For the perovskite silicon, or basically for silicon in the first place, we have the, let's say, issue that we use a lot of energy, and in turns we need highly sophisticated technology to make it work. also, this is a good technology. I think all of these technologies are highly promising, and we certainly should not wait until perovskite or perovskite-organic or perovskite solar cells are good. So we should put everything with silicon that we can do, and then just add all of the perovskite and all of the perovskite-organic, also the pure organic solar cells to the mixture, because yeah, well, I just read a study from EAI. So International Energy, or what? I don't know the last word anymore, but basically the administration thinking about calculating scenarios how we can achieve net zero in the next 30 years, and we basically have not only to double, but we have to bring up photovoltaics by an order of magnitude. So we need everything that we can get. So I won't say anything is better. We need all of them, and just throw it out there.
Thank you for the answer. Let's move to the next one from Nisheka. What is the thickness of moly oxide and C60 layers respectively? In your Tandem paper, which got published in April, you have shown AZO nanoparticle as interconnect in the air. Can you please tell which work is better? Also, reports are there about interconnect layers using sputtering such as ITO, IZO, AZO. In your opinion, what works better?
So the first part I can answer very quickly. So molybdenum oxide is 20 nanometers. C60 is not there, so we're using PCBM, but PCBM is actually quite thick, so we have 100 nanometers. Good thing is that PCBM is not absorbing in the infrared, so we can make it as thick as we want. It will not steal us any light. I think regarding the interconnect from our paper, there's actually a misconception, because I'm pretty sure that AZO nanoparticles don't work as an interconnect. So we tried it out and it doesn't. So in the publication from April, we actually showed the interconnect that I was promoting today. And yeah, well, since you are asking me, I of course think that the indium oxide is the best interconnect that we currently have. So I think that there's basically no better way to do it at the moment. So you can also do it with sputtered ITO. With sputtered ITO, you always have the problem that you're punching through the first layers. So you're punching through maybe the IZO or the BCP that you're putting on top. You are limited in terms of thickness, so you need some nucleation. So typically, I think the lowest that there is at the moment is something like 7 or 10 nanometers of ITO sputtered, where we are at 1.5 nanometers of indium oxide, which is nice in terms of pricing. It's also nice in terms of optics. So we have almost no optical absorption, as you have seen, due to the indium oxide. Yeah, once again, I think AZO, you would really have to dope it like crazy to work as a real interconnect. There might be some weird, I'm sorry. You might have it work if you really dope it like crazy, but I'm not sure if this will be viable on top of a perovskite solar cell. I hope I answered your question with this.
Thank you very much for the answer. Let's move to the next one from Siddharth. It was nice knowledge gaining by you. How can we say that the perovskites are good over Hassler compounds?
Okay, this would actually be something I have to Google, because George, do you know these Hassler compounds? You're talking to an electrical engineer here, so I'm guilty as charged. I don't know them. Maybe Siddharth, can you maybe elaborate a little bit on what kind of material you are meaning?
Maybe I will try to unmute this person so he can explain us. Give me 1 sec. Hello?
Hello. Am I audible to you?
Yes.
Hello.
Can you
Yeah.
please explain or elaborate a bit?
Yeah, definitely. One of my senior is working on the half Husserl and Husserl compound, which are also good for the photovoltaic application. That is why I wanted to ask, are these compounds are also in the trend or a future for the photovoltaic field, or just like we can carry on with the perovskites kind of compounds?
Yeah, as you recognize, both George and me have never heard of the name. Probably then they're currently not
Okay,
trending.
okay,
I'm
okay.
sorry.
It's perfectly all right, because I also heard that very first time, because since my master's I am working on the perovskite materials. That is why I was wondering more I am the only one who is not knowing the exact Husserl compounds and all. That's it. Okay, thank you so much.
Okay, I will just look it up soon, but you're telling me something new here.
Okay.
Maybe it's the
Yeah.
next big thing. Maybe, I don't know.
Thank
Yeah.
you.
I also did not hear about this. That is why I thought to, ask about this. That's
Okay,
it.
thank you.
Thank you. So let's move to the next one. From Nisheka. Have you tried to make perovskite-organic tandems in NIP configuration? If yes, do you have any recommendation about ETL for organic cell other than C60, such that it protects the underlying perovskite cell?
Yeah, actually, no, we did not. So we did not do an NIP, mainly PIM. Oh, wait a second, NIP. I'm just mixing stuff up at the moment. Main reason is that there's a lack of these barrier layers from ALD done in as a PET semiconductor. So I know that there was some approaches from Stacy Band where I think Jimmy was it, who was trying to do some vanadium oxide from ALD to get a barrier on top of there, but I didn't hear from them in a long time, so I'm not sure if this actually played out. In our lab, we would actually the main problem would be the stability. I know that there's some that it would be nice to use maybe the tin oxide there as an end contact for the organic solar cell, but also the organic solar cells with tin oxide as an end contact. So ALD tin oxide, at the moment, they are not as efficient as the PIN structures. So we're a little bit limited there, but we are working on it. But I cannot give you the perfect recommendation because I think the best solar cells with NIP structure are currently at 20-21% or something like this.
Okay, thank you very much for the answer. Another question from Felix Utama. Very impressive work, well done. If I understand it correctly, your indium oxide is not stoichiometric, not indium oxide, indium 2 oxide 3. Was this a deliberate decision to increase the charge carrier density or maybe for another purpose?
Short answer, yes. It's self-doping by oxygen deficiency, and that's the main reason why the interconnect works. So we want it to be less than 3 oxygen there.
Thank you for the answer. And I can see a hand raised from Konstantinos.
Thank you very much for this very nice presentation. I have managed to follow you from the middle towards the end. I have 2 questions. The first one is just a little bit to reconfirm something. And the second one is like to learn how do you select materials regarding this interface material in these 2 terminal devices. So starting from the second one, I mean, if you try to pass, from the electrical circuits, if you try to pass a current from one circuit to another, in order to minimize the losses, you should match the output resistance of the circuit that the current is passing to the matching resistance of the material that it comes. In this case, you are minimizing the losses. You maximize the transfer. Regarding you are maximizing the electrical matching of the 2 things. So in your case, how did you regulate this?
Actually, we are not. We're in these kind of devices. We are typically not talking about resistances, so not right in intake or output resistance. But since we are typically talking on the charge carrier level, we are more talking about barriers and how to overcome them. Since we're typically not talking about ohmic resistance. So ohmic resistance is by far not the worst issue that we have in these kind of solar cells. You can just think about that. We're talking about layer thicknesses of overall below a micron. So the ohmic resistance needs to be very, very severe in order to actually impact these kinds of devices. But something that seriously impacts it is are these barriers. So we are typically stacking. So in our case, for example, we have an N contact on the top. So if you're talking about PIN structures, you have an N contact on the top, and we are processing a P contact on top. And they typically form a junction. So we have, if we go for thermodynamic equilibrium, we have charge carriers going from the low work function to the high work function material, forming this kind of a Schottky barrier, which is much, much worse than anything ohmic that we can get. And the choice of material in our case is the size of this barrier. So the width is determined by the so-called Debye length, which is then determined by 1 over square root of charge carrier density. And we are basically bringing this barrier as narrow as possible, so that we are talking about distances of so in our case, actually, when we do the indium oxide there, we were not able to see it in the first place. So it was so narrow that even with UPS, you were not able to probe this barrier anymore. And then we have a tunneling through the barrier. But we are typically not so much concerned about the resistances. Of course, I think if we would really go for the 30% in the end, the mobility differences inside the perovskite and inside the organics, they will give maybe some kind of an issue. But we didn't run into this limitation so far. I think it may also be because the thickness of the perovskite is much more than the thickness of the organics, and eventually the distances to travel is lower. Did I answer your question?
Yeah, yes. I think that you are right, that you have barriers because of the energy difference, that to address the conductivity mismatching, the resistance mismatching. Am I right? So it's
it's not really
the energy barrier.
I wouldn't anymore say that it's a resistance mismatching. It's actually an energy mismatch.
Yeah.
And then if I think maybe in the future something that could be an issue is this resistance mismatch, but we are by far not on the point where this will be an issue.
Yes, and something else just to mention about some type of losses when you have your 4-terminal device. Mainly, you mentioned optical losses. This has to do with the difference of the refractive indices that is exhibited between the different materials in the 4-terminal device.
Yes, and additionally, we have to build. So in our case, we were fine with 1.5 nanometers of indium oxide. If we would go for a 4-terminal device, we would have to add, so we would not have an interconnect here of 1.5 nanometers, but we would have to have a semi-transparent electrode. Then we have air or some kind of liquid that matches the refractive index. And then I have to have another semi-transparent electrode, which typically means that you need at least 100 or 150 nanometers of ITO, where then the absorption is not 0 anymore. So in our interconnect, the absorption is not 0, but it's so thin that you don't see the absorption anymore. But if we're talking about 300 nanometers of ITO, we have absorption. We have no chance of getting around this. So this is a loss that we cannot mitigate. We can optimize them a little bit so that the absorption of the ITO is maybe shifted more into the blue region, so that we have the high transmittance in the infrared region, but still it never gets optimal. So we have this optical optimization that you talked about, and we also have this index matching, and we have additionally the absorption losses in the electrodes. Both of them are not fundamental, but pretty fundamental limits, because you need the electrodes to be conductive. And the bigger the cell gets, the worse is your problem, because at some point you have to put grid fingers in the middle, which is even worse.
Thank you very much, sir.
Thank you very much, Konstantinos, for the question, and Kai Olivier for the comment, for the answer. So I cannot see any other question. We have still 1 minute, so I would like to ask you as well one question out of curiosity mainly. So I have seen the efficiency of organic solar cell, at least maybe the non-certified values, maybe reaching around 90% recently. So have you used similar materials or device configuration with them, or your results are based on a binary concept?
So we are using ternary concepts for mainly for the sake of stability. Actually, also the ternary junctions are also giving a little bit more of an efficiency, a current boost in the near infrared. So it actually helps the tandem a little bit. But these were all the results that you just saw were with old, or say like PM6, Y6 with a little bit of PCBM, like the old school non-Fourier acceptors. We are currently working on it, but
I have seen some new materials that they at least promise some increased PCE. So what is your opinion on this?
We're currently waiting for these materials, to say it like this. We are just waiting for them to arrive. We will certainly integrate them into our devices. We also will have to modify the wide bandgap solar cell a little bit, but this is certainly something that we will look into it, because also those kinds of those solar cells promise to have a slightly lower energy gap, and so of course every step here to the left that at the same time maybe even gives us efficiency is like doubling the things that we can do with these materials.
Thank you for the answer. And my last one, if I may, is what is your opinion on adding a third cell in the tandem, like make a three, like a tandem cell with 3 junctions? What is your opinion on this? What are the limitations?
I love it. I love the idea. So we are, another thing that we are working on. Thing is that the devices are getting more and more complex, of course. I know that Juncker is so from the University of Eindhoven, I think they're pretty successfully currently working on triple junctions. So I think on this year's MRS, I love the idea. It's what we have to do in the end, right? So we don't want to stay at 2 terminals. We want to build triple junctions, quadruple junctions. In the end.
What is your opinion? I mean, do you have any feeling what might be the optimum, like combining perovskite organics or even silicon perovskite organics? What is your opinion on this?
I think so. We didn't try it so far, but I think that it will be very hard to combine a perovskite organic tandem with the silicon, because we would have to flip it around. So we have to process on top of the silicon. So we would have to process the organics, and typically the organics, they really don't like the ALD process. So typically you want the ALD process to happen before the organic on top of the perovskite. Maybe we will be able to stabilize organic for ALD processes in the future, but at the moment these are a limitation. In general, for thin film triple junctions, I think the main limitations in terms of organics will be the energy gap. So again, the same issue that we have here. Also here we would need these 1.1, 1.15 electron volts for really high efficiency triple junctions with organics. There perovskite tandems have an advantage at the moment. Once again, I don't think I can tell you too much, but I think there will be a talk on the MRS fall meeting from the guys from Eindhoven showing the current progress in this topic. But I think that one of the tricks will be the ALD. So if you are able to build the ALD on the right spot, and you're able to protect each layer each process from the next, as soon as your ALD layer is on top, you can process the next cell. And if you're able to put your ALD layer on there, you can process the next cell. And like this, you should be able to basically continue forever. But of course, it will make the device more and more complex. And in the end, we will have to calculate a trade-off. So how much energy, how much time, how much complexity can we afford if we still want to talk about a low price product. So we still want to sell cheap solar cells, right? And so if we are placing, I don't know, 10 solar cells on top of another, we might end up with a problem.
Yes, I agree with you, but maybe for this tandem, since they provide high voltages, maybe they unlock some interesting applications, for example, like solar fuels and this kind of topics. So maybe even they might be expensive, they might be also very, very useful in the future.
Yeah, so I would say if you're able to go there, I think they might be also very interesting for space. So I don't know about the organics, but for very, very importantly, the perovskites, since every gram is important. If we go to space, then we want the highest efficiency that we can get, and no matter the money that we have to spend there. Same as for gallium arsenide and all the 3.5s that we're using at the moment.
Okay, great. So I can't see any other question or comment in the chat or any hand raised. So I would like to thank you very much, Kai. It was a great pleasure and honor for us. We learned a lot from your very interesting and detailed presentation. So
you're for listening.
It's time to move on to the next presentation. And as I mentioned earlier today, unfortunately, Mike Lirwin is not able to give this presentation today due to unforeseen circumstances for him. So in order not to have a gap in the agenda, I decided to, at least I tried to extend my own presentation from the morning session, and to give you an introduction about how to use carbon-based materials also for the transparent electrodes. So give me a minute until I share my slides. Okay, so I hope you can see my screen. Is it correct? Yes? Okay, so as I mentioned, I have to cover the topic that was supposed to be presented by Cubic PV and Mike Lirwin. So of course I'm not able to present about the silicon perovskite tandem. So I decided to extend my earlier presentation about the use of carbon-based materials. So and I will try to give you an idea on how to use these carbon-based materials as transparent electrodes. So yeah, as I discussed in my presentation earlier today, the three main costs of a typical perovskite solar cell or perovskite solar panel in a theoretical model, of course, it is the gold and the HCl, but the main one is the transparent conductive oxide, because it has also the glass substrate, and also the processing for example, in a module to make the P1 step, and also deposition, of course, of the indium tin oxide or fluorine doped tin oxide, which is performed by sputtering process. So it's quite an energy and time-consuming process. Of course, when we switch to an carbon-based perovskite cell, and especially in this graph here, it is considered the HTM-free triple meso. So we have, as I presented earlier today, a compact titanium dioxide. Just a moment. A compact titanium dioxide sintered on top of fluorine doped tin oxide, glass substrate. Then we have a mesoporous titania grown on top, a mesoporous zirconia grown on top of the titania, a mesoporous carbon layer deposited on top of the titania zirconia, then sinter all this structure together to form a mesoporous triple junction structure, and then the perovskite is infiltrated through this porous network to form the final perovskite cell. In this case, in the absence of metal electrode and in the absence of any HTM, and we have already presented that it is possible to reach maybe, I think the world record for this type of device is a little bit more than 15 or 16%. You really, minimize the cost of your device to actually the cost of the transparent conductive oxide and the substrate. And because, as you probably already know, the ETL is very cheap and is also solution processed. Same for the perovskite absorber, same for the carbon electrode and the deposition of all these layers. So there is then the limitation on how we can find a way to make alternative materials, and especially if we want to consider flexible, photovoltaics like perovskite solar cells, maybe we have to switch from FTO or ITO to an alternative material to enable also bending capabilities of our devices. Or, for example, as in some smartphone, that they have the capability of flipping or bending the screen of the device. So if we want to go to this kind of functionalities, we have to get rid of the FTO or ITO layer. So one possible material that it has this kind of potential promises and interesting properties is graphene. So probably the most important of them is the high transparency, because graphene is one of the most transparent materials. It has around 97.7% transparency for a single layer graphene. And also it has very high mobility, and we can engineer the material to perform as a very highly conductive material, but also at the same time it's a very strong and lightweight material, so we can stress it by different like bending cycles or bending and stressing. The material, this kind of material is very, very tolerant to this type of stress tests. Of course, as it is probably, as you probably already know, one of the most common ways to make graphene, but in this case only for small area, is the Scotch tape method, which is the method that first presented the the first demonstration of graphene and its application for its fantastic electronic properties. But with this kind of method, there is no possibility for large area deposition and high throughput. So in this type of method, we can only make some devices such as graphene GFET, graphene field effect transistor, or this kind of things with a very tiny, very tiny active area, as you can see in this slide. So then what type of graphene can we use in order to exploit the fantastic properties of graphene as transparent conductive electrode? And this is summarized actually in this graph. There are actually many different methods on how to produce graphene. One of them is the chemical vapor deposition method, when we actually use methane in order to grow graphene on a catalyst substrate. Other methods include reduction of graphene oxide, of course, the liquid phase exfoliation, such as the method that I presented earlier today, and other synthetic approaches. Of course, the only, at least up to date, the only way to make highly conductive and transparent at the same time graphene is by using the CVD grown method. And as you can see here, after doping the CVD graphene, it is possible to reach close to 10 ohm per square for around 90 to 95% around 90 to 95% transparency. Of course, I mean comparing graphene with other type of possible materials that can be used on a flexible substrate. You can see that, of course, ITO is the main material, but it has its limitations, as we explained, as I explained to you before. So graphene has a potential to be used mainly for flexible large area devices. Of course, and other promising materials include silver nanowires or copper nanowires probably, but the main problem about this material is that if you want to make perovskite solar cells with these electrodes, you may face a problem of metal halide degradation of your perovskite material. So graphene might be a very, very good choice for stable and large area flexible devices. So how to grow then graphene and transfer it to a substrate? As I mentioned today, in order to grow CVD graphene, we are using obviously chemical vapor deposition of methane on a copper substrate. Then practically we spin coat some dielectric, like for example PMMA on top by spin coating, and then we attach this kind of structure to a substrate, for example, a flexible substrate or a glass substrate, and then we immerse it in some copper etchant in order to remove the copper foil from graphene, and then we let's say force the etched graphene PMMA structure on top of the desired substrate, and then we wash out PMMA and we remove the substrate. So at the end of the day, graphene stays on top of PMMA, and then we add this kind of graphene PMMA on top of any substrate that we desire, and it remains on our desired substrate that can be used for any kind of application. So this is one of the most promising, let's say, demonstrations that happened quite a lot of time ago, when people actually they were trying to make demonstration of graphene for its fantastic optoelectronic and electronic properties. A group from South Korea, from SKKU, they demonstrated a method for the large area deposition and at the same time transfer on flexible substrates of up to 30-inch single or double layer CVD graphene, and they also demonstrated some interesting display properties. So as I already mentioned to you, graphene at a single layer level has a very high transparency, around 97.4%. So it is very difficult to beat in terms of transparency, and especially if you go even to longer wavelengths. If you compare it with ITO or FTO, it will the difference will be even much higher compared to these benchmark materials used for photovoltaics. And the point is that in order to achieve high conductivity and low sheet resistance for this type of material, we have to stack additional layers, so second, third, or fourth layer, and then perform a doping process in order to improve, in order to increase the current density and reduce in this way the heat resistance of the material. And why is this? Because of this very peculiar property of graphene, that it has linear band structure. So if the graphene is undoped, so the Fermi level is positioned at the Dirac point. So the density of electrons in this point is very low. Thus, in order to improve its conductivity, we will have to somehow shift the Fermi level towards the conduction or the valence band. So this is what people from this group demonstrated, that it is possible to reach for this roll-to-roll graphene, 4-layer graphene, around 90% transparency for less than 30 ohm per square heat resistance, which was a very, very big breakthrough at that time. And here you see, I mean, the effect of adding additional layers on top of each other. So the first layer has around 250 ohm, and then if you add, I mean, more layers, the heat resistance will drop. And also the other point is that the effect of the doping is less prominent as we go from one to higher number of layers. Another very important topic that, of course, I mentioned already is the very stable structure of graphene, that is crackless material. And here it is demonstrated that even if we put high percentage of strain, so for example, here it is shown up to 6%, which is a high number actually, the graphene electrical properties remain unchanged, while in the case of the indium tin oxide, if you go above 2.5% of strain, the material starts to crack and it has an irreversible degradation of its electrical conductivity. So the people from this group demonstrated a big variety of different kind of p-type dopants, and it has been in this paper it has been shown that the best one, according to this work, is the gold fluoride in nitromethane, that it can reduce the heat resistance of pristine graphene in the single layer, of course, level of up to close 90%. So what does it mean? If it has around 1000 ohm per square, it will go down to 100. So let's move forward. Another very interesting work has been done from people in CNR in Italy at the University of Bari. So they also presented some very interesting, data using, instead of gold chloride, thionyl chloride, which is another chloride material, and they used this type of system to dope all the way from a single up to 5 layers of graphene. And in their case, they demonstrated a heat resistance of a little bit less than 20, between 15 and 20 ohm per square, which is a very, very good number. It already matches the heat resistance of the typical ITO that is used currently for photovoltaic applications, and combined with a transparency of about 85, I would say, percent, or close to even higher, maybe 87%, which is a pretty good value, I would say, as if you benchmark this kind of material with the typical ITO. And here you see a typical image of the transparent conductive electrode based on CVD graphene, and some interesting application of this kind of systems. So it seems that as you probably already know, graphene is a very good material for sensing, because it reacts with most actually of the external triggers that you put on top of this very peculiar material. So I mean, people in the literature were able to find many different ways to dope graphene, but of course, what we have to consider, which is very important, as a very important figure of merit is the stability, of course, of this doping. That sometimes, for example, with the chemical doping might not be straightforward, because if, for example, this ghost doping is exposed to high temperature, maybe the conductivity will reduce or the sheet resistance will go back to its pristine state. So we have to find a method to attain a very stable doping. So in the first example, I would like to present you here, people from the literature, they managed to make application of this type of material, the CVD graphene doped with gold chloride, and they built a flexible perovskite solar cell on top of PET substrate, but at the same time they used a treatment, an uptest treatment, in order to make the adhesion of this type of system much better on top of the PET substrate. And as you can see, for example, here, the sheet resistance of the 4-point probe heat resistance measured, for ITO was around 10 ohm per square, and for single layer graphene, it is around 80 to 85 ohm per square. So it not so good as ITO, but still it's significantly lower compared to a typical undoped CVD graphene. And of course, you see here the huge difference between the mobility, which plays a very important role as well in the photovoltaics for a current collection. You see the typical mobility for ITO is 30 centimeter volt second, while for the graphene is around 500. And this is because it is doped. If it is undoped, the mobility can be up to 10,000 of a square centimeter per volt second. Then moving forward, what these people have done in this work, they managed to demonstrate quite efficient, I would say, perovskite cells using this type of treated CVD graphene on top of PET perovskite solar cell based on very typical at that time device configuration that is called PIN, and P is the P.PSS. The perovskite material was the methylammonium lead iodide and was PCBM, and the electrode was aluminum. And as you can see, using two different types of perovskite, for mamidinium mixed iodide bromide, they managed to achieve efficiencies of up to 18%, and for typical methylammonium lead iodide up to 16%. Of course, as you can see here, for typical ITO devices, because the sheet resistance of ITO on top of a flexible substrate is not the same as on glass substrate, it can be significantly increased. The efficiency of this type of photovoltaic device is actually similar and at the same value, around 16%. So here it is shown very clearly the big advantage of graphene when it is used as a transparent electrode, especially for flexible perovskite solar cells. And as I already presented before, here also, these authors, they demonstrate the tolerance of this kind of material on the bending cycles. Of course, you see here a very big stress test of up to 2 millimeter curvature. You see that in the case of ITO, you have an irreversible degradation. Still, when you have only silver chloride, there is some irreversible degradation. But when there is this binding modification to bind the graphene on top of the substrate, this I mean degradation of the conductivity or the resistivity of the material is actually almost fully suppressed. And the same for bending cycles. You see ITO have significantly higher bending cycle tolerance compared to the CVD graphene. And you see here also actually the cracks that are formed for ITO, while in the case of graphene, there is no difference before and after this bending. Another very important material that can be used as a dopant for graphene is molybdenum oxide. And why this is important? Because actually it is already being used, especially in organic photovoltaics, as a P-type material, and many people is using moly oxide. Also, as you probably have already seen in the previous presentation, molybdenum oxide was used also for tandems. It happened to be a very promising material also for graphene doping, and actually not only doping, but making it surface hydrophobic, because we have a very important problem when we are making devices based on graphene, especially when these devices are solution processed. So what is the problem? When you want, for example, to deposit aqueous solution on top of graphene, this might be very tricky because graphene is very hydrophobic, as you can see here. But when you process your graphene with moly oxide, so when you deposit a thin film, even I think, as you can see here, 1 or 2 nanometers thick moly oxide coated graphene can planarize and can make its surface very hydrophilic. Of course, UV ozone is another method of making surfaces hydrophilic, but we are very unlucky here, because if you process your graphene with UV ozone, you will irreversible damage and introduce defects, so it will affect its conductivity and its graphene's mobility. So here you see the cross sections of the 2 different devices that have been prepared in this work. And actually, it was very interesting to see that, it was possible to obtain also very, very high efficiencies, around 17%, for flexible perovskite solar cells based on graphene, molybdenum oxide doped graphene electrodes deposited on top of PEN substrates. So very, very promising results, especially regarding the flexible perovskite cells. And the same thing is presented here for this work, that in the case of another, bending test performed for the 2 different electrode materials, graphene and ITO, graphene clearly outperforms the typical ITO regarding the bending test. And here you see again this crack formation for ITO, while for the graphene case, there is no, irreversible degradation of the material. Another important work that has been presented, recently, it points out, again using gold chloride, points out not only the conductivity, but also the shift in Fermi level, so the work function of the material, that can be also beneficial when you make devices that it is not possible in the case of typical ITO or FTO, because the Fermi level or work function for this type of materials is fixed. While if you have graphene, as I presented you before, maybe I can go a little bit back in here. As you can see, because of this peculiar nature of its graphene band structure, you can actually shift the Fermi level, thus the work function of the material, according to your desire, by selecting the proper doping element. So what these people have done here, they have demonstrated that by changing actually the concentration of this type of dopant solution, they were able to tune yes, here it can be clearly seen, they can tune not only and decrease not only the the seed resistance of this type of material, but it is already presented in another work earlier, but also in this case, it is possible to tune according to our needs. For example, if you want to make an LED or a photovoltaic device or another device of your preference, or use some specific kind of material that they have some specific functionality, for example, replace ITO with another one, or make transparent solar cells or something like this, and your material has some specific work function. What you can actually do with graphene and with the dopants, that if you properly select them, you can tune its work function to your desired level. So of course there is a limit. There is a limit which probably is around maybe 5 electrovolts or so, but still there is a huge tunability regarding the work function of CVD graphene. And the same, of course, for the seed resistance, but most of the applications would require low seed resistance. And of course, as you can see here, for example, this tunability of the work function and also the seed resistance gives rise to higher performances, up to 18% in this case. And also, in order to make clear that this kind of doping is stable enough, people have also demonstrated light soaking tests in order to make clear that the the stability of the transparent electrode itself, because if you compare these two actually plots, the only difference in the device structure is that in one case we have glass and ITO, in the other case we have glass plus graphene as the electrode, and all the other device configuration is the same. So we have seen that in this case the stability of both systems is more or less the same. And finally, there is another work that has been presented recently in the literature, and it has to be with molecular, in this case, doping of graphene with TFSA. I'm not 100% sure about what is the what TFSA stands for, but this is a molecular material that is capable of functioning as a ghost dopant, as a molecular dopant for graphene. And in this case, the people, they have demonstrated also that it is possible not only to change the seed resistance, but also to shift the Fermi level according to the needs of your device. And they have also demonstrated again the tunability of the work function, and also, of course, the carrier concentration. And as well, another very important point that it hasn't been presented before is that, of course, as we increase the concentration of the dopant, there is a high risk of decreasing the transparency, because actually we add some ghost, some dopant on top of graphene. And as you can see here, even at the 30 millimolar concentration, there is less than probably half or maximum 1% drop in the transparency of the graphene film. But at the same time, this treatment gives rise to maybe close to 5 or 10 times lower seed resistance, which is significantly outperforms the loss from the optical transparency. And another point that has been discussed, and it was a very big topic in the beginning of this research field about using graphene and doping graphene. They have also demonstrated that this type of doping is super stable, because with the acid doping that was presented in the first paper from the Korean group, which was not very stable, especially for high temperature or long exposure. With this one, the TFSA doping can be very stable, even up to, at least they have demonstrated, up to 20 days of continuous monitoring the heat resistance of the material. And so just to make the long story short, they were able, by tuning the graphene's Fermi level, and at the same time, as I presented before, heat resistance, they were able to make some very highly efficient graphene-based flexible perovskite solar cells with efficiencies of above 18%, and some very durable devices that can sustain or maintain up to 95% of their initial power conversion efficiency for more than 1,000 hours, which is actually a very good result for this kind of devices. And here are also some more information about the photovoltaic characteristics of this type of systems. So maybe in the next, I have still 5 minutes, but maybe I can conclude the presentation by saying that, let's say, trying to summarize now both the presentations. I mean, graphene seems to be a very interesting platform for making photovoltaic devices, and especially the electrode materials for photovoltaic devices. If we consider, I mean, the solution processability in the first case, that we would like to make fully printable photovoltaics, but also at the same time, there is a possibility, if we want to build flexible perovskite solar panels, to replace FTO and make our I mean, even stretchable photovoltaics, even wearable photovoltaics, or bendable photovoltaic devices, integrating them in some portable electronic devices. It is possible to do it with, after replacing the transparent electrode, that we have demonstrated that when we use ITO, it's not possible to have these functionalities. But if we change the electrode with graphene, and especially with CVD graphene, of course, it would be even much more favorable if we will be able to do it with solution processed graphene, but up to now it's not possible. So with this type of graphene, plus of course the doping process that I described to you today, it is possible to make and add functionalities to this kind of photovoltaic devices, such as flexibility, stretchability, lightweight, and bendability, bendable and very durable devices. So summarizing then, carbon-based materials are very promising to solve some problems in this type of solution process photovoltaics, but of course they have to be, I mean, properly engineered. So for example, in the case of the solution process, you have to find a method for properly controlling the morphology, as I showed you in the first part of my lecture, or in the second part, you have to properly find a way to dope graphene in a way that it is tuning both, I mean, the Fermi level according to your needs, or reducing the heat resistance according to the application you would like to apply, and at the same time, finding a method that is stable and durable. So with this, I would like to thank, of course, I mean, my funding source for my project, Marie Sklotovska's reactions, and my individual fellowship from European Commission Horizon Europe 2020. And I would like also to thank you for your attention, and I'm very happy to ask any question and start the discussion. Thank you very much.
So I can see a question, George, for you from Jeffrey Gordon. I don't know if you can hear me.
Yes, I can.
All right, excellent. And the question has to do, since few layer graphene, say 4 to 10 layers, has a scalable production method, whereas there are no scalable production procedures for graphene. Would few layer graphene provide an adequate coating for the same objective?
So I'm not really sure which few layer graphene Mr. Jeffrey Gordon refers to, but so in this case, the first procedure that I described to prepare the few layer graphene is solution process. So it is not a continuous film in order to make the transparent electrode. So
George, I have asked Jeffrey Gordon probably to unmute himself.
Yes,
and make
maybe it would be easier for us.
Yes, thank you.
Hello?
Yes, thank you. All I meant is that few layer graphene can be produced in a scalable method, unlike the methods that you described. Now, it has different optical properties, different electrical properties, but given the enormous practical advantage of mass production, I'm asking whether it might be an adequate substitute for pure graphene, clearly inferior in terms of the physics and chemistry, but would it be adequate for the cell performance you have in mind?
So the simple question is, each type of material has its own applications, I would say, because the few layer graphene produced by solution, it's more favorable if you would like to use it for printing some electrode, but this type of electrode cannot be highly transparent because this type of material is in a nanoplatelet form. And in order to make a continuous film, you have to be above the percolation threshold. And in this case, it has to be few, probably tens or hundreds of nanometers. So in this case, the graphene is not transparent. So, but if you would like to add the transparency in your graphene, then you have to switch to CVD graphene. So then, of course, the cost, as you already mentioned, and the scalability is not already there, but researchers and companies in the field are working towards making this type of method even, let's say, scalable and cost-effective.
Okay, thank you.
Thank you for the question.
I cannot see, George, any other question. So I suspect everyone since the morning is
Yes, probably they were waiting to hear Dr. Michael Irwin and his interesting talk about the tandems, but unfortunately it wasn't possible. So I think we can close this presentation here. Okay, so let's move to the, let me see the agenda. So I think we finalized all the all the talks for today's for the second day, which is was devoted for the energy harvesting devices, and then we can move to this discussion and summary. So I would like to ask you, Konstantinos, or anyone else that would like to comment or discuss about what we have learned, and maybe give us an insight about your opinion about the topics that we discussed.
So from my side, I did not have the chance to follow all the talks today because I was traveling from Athens to Crete. But I have to say that the three lectures that I have heard that were about solar harvesting devices, they were very interesting, and I think that they provide an overall picture of the latest research and technology that is available, at least in a research level, because we did not have the chance to hear the person from the market because of unfortunate, these events, are happening. So I'm looking forward for tomorrow to go to the detectors and photodetectors and the photoluminescence devices. I think that, George, tomorrow's agenda is very long. Also myself, I will try to record tonight my lecture also to provide it to you, or to provide it later on, because I have we have the visit of 30 US universities in our university, and as I'm responsible for the international relations office, I should be there. But I think George will manage together, during the morning session to arrange, the lecture program. So this is from my side. We have already uploaded the first day. I'm waiting to George to send me also the second day to upload it into the YouTube and send you both of the links to all of you. Thank you.
Thank you very much, Konstantinos. Yes, I agree with you. It was a very, let's say, informative kind of day with very nice lectures all the way from the single junction perovskites and let's say on how to master the, I would say, formulations of the perovskite and passivating the perovskites, bulk and surfaces, use the carbon electrodes, carbon-based materials, and also the very important points regarding the very important topics of the tandem cells, that is actually the future for photovoltaics, not only for the typical energy production, but also for using this type of systems for artificial photosynthesis and solar fuels. So I think it was very nice to hear this kind of lectures. So tomorrow we start again at 9 o'clock CET, and we have the other applications of this very fantastic fascinating optoelectronic materials, with all the way from the LEDs, detectors, sensors, and field effect transistors, and lasers actually. And so we will be very glad to have you again with us tomorrow. So there is a comment in the chat. You will get also the slides. Okay, so thanks a lot for being with us, and see you tomorrow. Bye.